Cosmology is a quite modern addition to the physical sciences. This is quite contradictory since some of the most ancient questions humanity has ever posed are among those cosmology answers. Does it exist in unbounded space in the universe? Has it always been present? Otherwise, from what point did it start? Will it stop at some time? From the dawn, people have been seeking to create a conceptual framework for grasping the world and how they fit into it. The first theories or models of this sort were myths, which we today regard as stupid or useless. These crude hypotheses, however, highlight how crucial it has always been to us as a species to consider the cosmos. Although modern cosmologists use quite different language and symbolism than our distant predecessors, their motivations are basically the same. In this movie, I give a brief summary of cosmology's historical evolution together with an explanation of some significant concepts. These fundamental ideas will be covered in more detail in the next movies, which will also be a useful starting point. Most prehistoric cosmologies are based on anthropomorphism, the way non-human entities are interpreted with human characteristics. While some say that a god or goddess can govern the dead physical world, others assert that deliberate entities inhabiting it can either help or harm humanity. Creation stories usually credit entities understandable to humans for starting the universe. Though they vary greatly, global creation myths have some shockingly similar aspects. First of all, their images usually reflect the idea of superb craftsmanship. Consequently, every society sees the beauty of the natural world as the result of the work of skilled artisans. Another recurrent picture is the emergence of order from chaos, which reflects the progressive organizing of human society. The concept that the universe operates like a biological process serves still another parallel. The most amazing stories come from myths, showing the universe beginning from an egg or seed. These tales abound in the Enuma Elish, a Babylonian adaptation of Genesis. This myth is thought to have originated in Sumeria around 1450 BCE. Its creation narrative tells us the sea represents primordial anarchy. Several gods, who reflect the fundamental components of the world, emerge from the sea, like the horizon and the sky. Tiamat, the sea goddess, dies as two of these gods battle. Marduk, the other god, creates the earth from her body. China also provides interesting graphics. One about the great Pangu. The universe began in this story as a huge egg. The giant slept inside the egg for thousands of years, but when he woke, he broke free and destroyed it. The earth was formed from the heavier, impure bits of the egg. The lighter, purer bits rose to create the heavens. Pangu raised his hands to the heavens while firmly anchored on the ground. The giants grew taller as the heavens soared higher, preserving their link to earth. Pangu died finally, but his body parts were still valuable. His left turned to the sun, his right eye became the moon, his sweat became rain, his hair grew to be earthy plants, and his bones became rocks. There are creation legends like civilizations. I need more space to incorporate them all here. Whether African, Asian, European, or American, it is amazing how many formal parallels these legends have. Greece was where Western science began. Of course, the Greeks had their own gods and stories, many of which they borrowed from neighboring societies. They developed a set of rules for scientific inquiry and these more traditional elements. Still vital to scientific theories, the Greeks first identified cause and effect. They also realized that we might explain and describe observed events using mathematical or geometric techniques instead of anthropomorphic ones. Particularly through Thales, 625–547 BCE, and Anaximander, 610–540 BCE, Cosmology became an acknowledged scientific field inside the general framework of rational thought evolved by the Greeks. The word cosmology comes from the Greek word cosmos, which describes the world as an ordered system or whole. Greek chaos, the reverse of cosmos, stresses harmony and order. Pythagoreans of the century BCE held that geometry and numbers could explain all natural events. Mathematical ideas and the belief that reason and logic could be applied to understand the physical world marked the start of the scientific age. In his exhaustive account of the universe's creation, Plato, 427 to 348 BCE, writes how a divine demiurge generates flawed physical representations of the structures exclusive to the world of ideas. The physical world is not timeless and unchangeable. The world of ideas is. Aristotle, 384-322 BCE, a pupil of Plato, developed a worldview based on these ideas whereby planets and stars in the distance move in perfect circles, expressing divine geometry. In Aristotle's universe, Earth resides in the center of a sphere. Beyond this point, the heavenly bodies follow their idealized circular motions. The section of this sphere that reaches the moon is the domain of change, the imperfect reality of Plato. During the Middle Ages, the Western European perspective was dominated by this one. However, the perfect circular motions of the universe did not match the astronomical data the Greeks acquired from the astronomical archives of Babylon and Egypt. Though Aristotle emphasized learning about the universe through observation and pure thought, a thorough mathematical model of the universe matching all available data wasn't developed until Ptolemy's Almagest, assembled in the 2nd century CE. Although it persisted in the Islamic world, Christian civilization lost most of the knowledge the Greeks had accumulated during the Dark Ages. As such, cosmological theory was rather constrained in Europe during the Middle Ages. Combining Christian theology with paganism using Aristotle's ideas, not yet available in Latin translation, in the Almagest, Thomas Aquinas, 1225-74, produced a synthesis that would shape Western thought until the 16th and 17th centuries. Usually attributed with demolishing the Aristotelian perspective is Nicholas Copernicus, 1473-1543. Ptolemy's Almagest was a complete theory, but since it used a different mathematical formula for every planet's motion, it didn't reflect an all-encompassing, uniting system. It described the phenomena of heavenly motion devoid of a justification. Copernicus aimed to devise a theory that equally applied to everything. He could move the Earth out of the center of the universe, albeit just in part. Johannes Kepler completely dismantled the Aristotelian system, 1571 to 1630. Needing an explanation for Tycho Brahe's 1546-1601 very accurate observations of planetary motion, Kepler replaced ellipses for Aristotle's divine circular orbits. Isaac Newton's appearance was an essential turning point in modern cosmology's evolution, 1642 to 1727. In his foundational Principia, 1687, Newton showed that a general law of gravitation produced Kepler's elliptical motions as an inevitable outcome. Newton restored the idealized domain of universal laws of motion, a Platonic level of reality. Newton's theory holds that the universe is like a large machine performing the consistent motions the Almighty Creator demands, both here. Absolute expressions of an all-pervading inner God are space and time. Newton's ideas dominated scientific opinion until the early 1900s. But by the 1800s, defects in the cosmic machine had surfaced. The first steps toward technology matched the development of a mechanistic viewpoint. The Industrial Revolution resulted from the fixation of scientists with engine and heat theory. According to the laws of thermodynamics, no engine can run without flaws for very long before malfunctioning. The heat death of the universe was popular during this era. or the idea that the universe would finally fade away like a bouncing ball, gradually losing energy and coming to rest. When Olbers, 1758–1840, developed a paradox bearing his name, even though many others, including Kepler, discussed it before him, Newton's cosmic engine took a fresh turn in 1826. Olbers's paradox results from the reason the night sky seems dark. Like a line of sight across an infinite forest, every line of sight from an observer should eventually hit a star in an infinite, unchanging universe. The night sky should thus be as bright as a typical star. We go through nighttime darkness as enough proof the universe is not limitless. Whether the universe is infinite or not, the part that reason can explain has grown with time. Aristotle thought that the orbit of the moon, only 400,000 kilometers, marked a basic limit the human mind could not understand. Copernicus and Kepler thought the limit lay in the boundary, billions of kilometers distant. In the 18th and 19th centuries, there was a belief that the Milky Way, considered at least 1 billion times larger than the solar system, constituted the whole universe. The theory refuted this idea by implying that many of the unusual spiral nebulae strewn over the heavens were far-off Milky Way-like objects. Later on, we would call these things galaxies. Early in the 20th century, these two opposing ideas engaged in a great debate that I will explore. Thanks mostly to Edwin Hubble, 1889–1953, we know that the Milky Way is only one of hundreds of billions of galaxies. The modern era of cosmology began with the rewriting of nature's laws at the start of the 20th century. Albert Einstein, 1879–1955, undermined Newton's theory of space and time by presenting the theory of relativity in 1905. Later, still, his general theory of relativity also replaced Newton's law of universal gravitation. The first notable works on relativistic cosmology were produced by Lemaitre, 1894–1966, de Sitter, 1872–1934, and Friedmann, 1888–1925, who developed a fresh and complex language for the mathematical description of the universe. Since modern cosmology is based on Einstein's theory, I will review it in most of the next movie. Still, observational astronomers rather than theoretical physicists drove the last steps toward the modern era. Edwin Hubble, who had only recently shown that our universe included many galaxies similar to the Milky Way, published observations that led to the discovery that our universe was expanding in 1929. 1965 saw Penzias and Wilson finally discover the cosmic microwave background, offering proof, or as near to evidence as you are likely to find, that the Big Bang was the primordial fireball from which our universe sprang. Published in 1915 and enabling a cogent mathematical description of the whole universe, Einstein's general theory of relativity signaled the beginning of the modern era of scientific cosmology. Einstein's theory links matter and motion properties with space and time deformations. This is important for cosmology since it helps us see space and time as dynamic participants in the universe's evolution rather than as absolute independent of material objects. General relativity clarifies the source of space and time and helps us grasp the universe's starting point. Based on Einstein's theory, the contemporary Big Bang model, which has evolved as the best theory explaining the expanding universe, this model holds that matter, energy, space, and time began as a primordial fireball of matter and radiation at very high temperatures and densities some 15 billion years ago. Soon after creation, the temperature dropped to 10 billion degrees, setting off nuclear reactions and producing the atoms that define our shared identity. The temperature dropped to a few thousand degrees after almost 300,000 years, releasing radiation we now identify as the cosmic microwave background. This explosion carried space and time as it cooled and rarefied the universe. Stars and galaxies sprang from condensation from the expanding gas and radiation cloud. Our modern universe consists of the leftovers of the Big Bang, smoke, and ashes. Most cosmologists agree it's accurate. It can clarify the most pertinent cosmological findings and our knowledge of the universe's bulk characteristics. Still, it's important to realize that the Big Bang is still under active development. Most modern cosmological research is driven by the need to fill the voids in this otherwise interesting framework. For instance, Einstein's theory falls apart at the beginning of the universe. Relativity theorists explain singularities, such as the Big Bang, as events whereby measured quantities run infinite, and mathematics collapses. Though we can grasp the expected evolution of the universe at a given moment in time, the singularity keeps us from deducing the original form of the universe from first principles. Therefore, unlike archaeologists trying to reconstruct a city from ruins, we must use observations rather than merely intellectual pieces. Today's cosmologists are compiling enormous volumes of complex data to assemble the universe's history. Over the past 2 decades, technological developments have hastened observational cosmology research to an astonishing degree, launching a golden age of cosmic discovery. As part of observational cosmology, large-scale maps of the galaxy distribution in space are being produced to highlight the incredible vast-scale structure of filaments and sheets. These studies improve the deep views of the Hubble Space Telescope. The Hubble Deep Field can see galaxies at distances so great that it has taken light a great part of the universe's age to reach us from them due to its extended exposure. These sorts of observations let us see how cosmic history develops. For instance, microwave astronomers can now produce pictures of the structure of the early universe by tracking ripples in the cosmic microwave background produced in the primordial fireball. 2 forthcoming satellite studies aiming at a more thorough investigation of these ripples over the next years are Planck Surveyor and MAP. These tests should close several knowledge gaps on the structure of the universe. Astronomical observations help us to determine the cosmic expansion rate and its time-varying fluctuations. They can also explore the geometry of space by applying the quite strong triangulating principle. Einstein's theory holds that since the gravity of big objects distorts space, light rays do not always travel in straight lines. Much like the surface of a sphere, this effect can cause the paths of parallel light rays to converge over cosmological distances to close space-time back on itself. It could also produce an open universe where light rays diverge. Between these 2 choices, the normal view of flat space uses Euclid's geometric guidelines. Which choices are right depends on the cosmic density of matter and energy, something the Big Bang theory cannot forecast. The Big Bang theory underwent a significant theoretical overhaul when particle physicists turned to cosmology in the early 1980s to try to grasp the features of matter at very high energies that particle accelerators could not reach. These thinkers realized that the early universe would undergo phase transitions, a sequence of sudden changes in a minuscule fraction of a second that would greatly hasten its expansion. This phase of inflation will presumably flatten the curvature of space, unequivocally suggesting that the universe will be flat. This conforms with the earlier discussed cosmic surveys. Recent theories hold that the universe is expanding faster than ever, suggesting the existence of an enigmatic dark energy left over from the past inflationary era. Cosmologists have also used modern supercomputers to examine how cosmic material condenses into stars and galaxies during the expansion and cooling processes of the universe. These computations indicate that this process requires large concentrations of exotic material dense enough to support the development of structure and dark enough to generate no starlight. We refer to this invisible substance as dark matter. Further supporting the Big Bang theory is the near agreement between computer forecasts of the produced structure and the vast maps produced by observers. Thanks to the interaction between these new theoretical ideas and new, high-quality observational data, cosmology has evolved from a merely theoretical domain into a thorough experimental science. This process started with Albert Einstein's contributions at the dawn of the 20th century. Everybody is aware of the gravitational influences. Things descend upon Earth when we drop them. Running a hilltop is more difficult than running downhill. But to a physicist, gravity is far more than just how it influences our daily lives. First, the scale of things under consideration determines the relevance of gravity. Tides result from the moon being pulled around the Earth by gravity and the Earth being pulled around the sun. In astronomy, gravity is ultimately the main force that acts. Understanding the universe thus depends on knowing gravity. One of the basic powers in nature is gravity. It represents everything's universal inclination to attract other matter. The four basic forces are magnetism, gravity, electromagnetism, and weak and strong nuclear forces. Gravity is universal, unlike electrical forces acting between charged bodies. Positive and negative are two varieties of electrical charges, though electrical forces can produce attraction between unlike charges, or repulsion between like charges. Gravity is always attractive. Cosmology depends thus on it quite importantly. In many respects, the force of gravity is shockingly weak. Most material bodies are held together by electrical forces, many orders of magnitude stronger than the gravitational forces between atoms. Nevertheless, despite its restrictions, gravity is the main force in astronomical situations, since astronomical bodies always have the same positive and negative charges and never influence each other with electrical forces. Since it combined apparently unrelated physical events, Isaac Newton's theory of universal gravitation was one of the first major advances in theoretical physics. Newtonian theory of mechanics is encoded in three fundamental laws. 1. Unless outside forces cause them to change their condition, all remain in either rest or uniform motion in a straight line. 2. The momentum change rate is found by the impressed force and the direction of the action of the force. 3. Every action produces an equal reaction always. These three basic laws of motion precisely explain the motion of celestial bodies and balls on a billiard table. Newton needed only to clarify gravity. Newton saw that a body in a circle, like the moon orbiting the Earth, feels a force oriented toward the center of motion, much like a weight spinning around one's head. This motion can be produced similarly to how gravity causes apples to descend from trees to Earth. The force must be pointed toward the Earth's center in both cases. Newton came upon the inverse square law, which holds that the square of the distance between two bodies plus the product of their masses determines the attractive force between them. Over a century earlier, the inverse square law of universal gravitation, which Newton's theory derived, triumphed in elucidating the laws of planetary motion unearthed by Johannes Kepler. This accomplishment was so outstanding that for more than 200 years, scientific theory was dominated by the idea of a universe run under Newton's laws of motion, until Albert Einstein arrived. Albert Einstein was born in Ulm, Germany, on March 14, 1879. His family soon moved to Munich, where he finished schooling. Not a particularly gifted student, the young Einstein dropped out of school entirely when his family moved to Italy in 1894. After failing the entrance exam, he was accepted to the Swiss Institute of Technology in Zurich in 1896. Although he excelled academically in Zurich, his extreme lethargy prevented no Swiss university from recruiting him. He left his academic path in 1902 to work for the Bern Patent Office. This paid well, since the responsibilities given to a junior patent clerk were not especially demanding. He had plenty of free time to think about physics. Einstein published his special theory of relativity in 1905. In human thought history, it is among the most important intellectual achievements. Even more remarkable is that Einstein kept working as a patent clerk while studying physics as a particularly demanding hobby. He also published groundbreaking research on Brownian motion, a phenomenon explaining how tiny particles wobble in the face of atomic collisions, and the photoelectric effect, a phenomenon driving multiple developments in quantum theory. However, Einstein's special theory of relativity beats his studies during this period and the work of his colleagues in mainstream physics, since he effectively rejected the notion that time is an immutable, absolute property applicable to everyone and everything. Most of us consider this to be an indisputable fact. Such great conceptual hurdles call for a genius to get over. Einstein's original hypothesis was not relativism. Almost 3 centuries ago, Galileo had expressed the basic concept. Galileo argued that only relative motion counts. Absolute motion cannot exist. He said you could not experiment in a sealed cabin moving constantly on a smooth lake. Naturally, given the ignorance of physics at the time, Galileo could only see a very small spectrum of experiments. Einstein's view of the principle of relativity holds that every observer in relative motion has to feel the same exact application of all natural laws. Einstein specifically found that this principle applied to James Clerk Maxwell's theory of electromagnetism, which clarifies the forces between the already mentioned charged bodies. Maxwell's theory leads one to see the speed of light in a vacuum as a universal constant, usually denoted by the letter c. Considering the relativity principle seriously means that independent of their state of motion, all observers should measure the same value of c. Though this seems basic enough, the consequences are radical in the extreme. In light signal exchange tests, Einstein asked himself specific questions. He carried out a lot of Gedanken, thought tests. Imagine, for example, a train carriage headed down a track carrying a flashbulb in the middle. It illuminates 1 clock at each end of the carriage. From the standpoint of the seated passengers, should the flash go out, the light signal simultaneously reaches both ends of the carriage. Every clock displays precisely the same time. Consider the point of view of a stationary trackside spectator observing the train. Our frame of reference moves at the same speed as the light flashes for the passengers. Still, the rear passengers enter the signal while the front ones leave. This observer thus argues that the train's back clock illuminates before the front clock. When it lights up, the front clock shows the same time as the rear clock, though. The spectator guesses that the train clocks are broken. This example shows how arbitrary the meaning of simultaneity is. Though they show up at different points in the track's frame, the 2 light flashes land simultaneously in the carriage's frame. 2 further strange relativistic events are length contraction, moving rulers seem shorter, and time dilation, moving clocks seem to run slowly. All these results follow the presumption that all observers constantly measure light speed. Obviously, some of the above are impractical. The velocities have to be a considerable fraction of c if they are to be clearly observable. Such speeds are unlikely for railway carriages. Experiments have shown time dilation effects exist. With their slow internal clock, radioactive particles decay more slowly at high velocities. Inspired also by special relativity, MC2 is the most well-known physics equation showing the equivalency of matter and energy. Experiments have used this equation to test the theory underlying atomic and chemical explosives. Although Newton's The Laws of Nature mostly concentrate on the causes and effects of different velocities, it is interesting that the special theory only considers bodies continuously moving around one another. Newton's second law addresses an object's acceleration, its rate of change and momentum. Special relativity only addresses inertial or particle motions without external forces. It cannot explain the accelerated motion of any sort, and motion affected by gravity. Einstein had a deep insight on how to harmonize relativity theory with gravitation. First, we have to take Newton's theory of gravity into account. This view holds that the square of the distance between two particles and the product of their respective masses define the force. One particle of mass m generates on another particle of mass m. Newton's laws of motion indicate that this accelerates the first particle, as shown by F, ma. This equation relates the particle's inertial mass, m, to its resistance to acceleration. Nonetheless, the mass m, in the inverse square law of gravity, measures the response of one particle to the gravitational force produced by another. Hence, we refer to it as passive gravitational mass. Newton's third law of motion, however, states that should body A generate a force, body B will exert an equal and opposite force on body A. Furthermore, the charge of the particle, that of active gravitational mass, must be m. Newton's theory regards all three masses, inertial, active, and passive gravitational, as equivalent. Still, there doesn't seem to be any evidence supporting this. Could they not be different? Einstein contended that this equivalency had to come from a more basic concept, the principle. Saying, all local, freely falling laboratories are equivalent to the performance of all physical experiments, he suggested that traveling between accelerated frames of reference produces gravity rather than a natural force. Imagine an elevator with a physics lab to help one to grasp how this is feasible. If the lift rests on the ground floor, experiments will demonstrate to the passengers the presence of gravity. For example, fastening the weight to the lift ceiling will stretch the spring downward. Imagine us riding the elevator to the top of a building and letting it drop free. Inside the freely descending lift, you cannot sense gravity. The weight falls concurrently. Thus, the spring does not extend even if the speed of the lift changes. This would happen with the lift in space far beyond Earth's gravitational force. Consequently, the absence of gravity is rather similar to the condition of free fall in response to a gravitational force. Imagine a scenario in which we fastened a rocket to our lift in space above gravitational force. If we fired the rocket, the lift would accelerate quickly. In free space, there is no such thing as up or down. Hence, attaching the rocket would cause the lift to accelerate in the opposite direction toward the ceiling. What is spring like? The acceleration stretches the spring toward the floor, shifting the weight in the opposite direction of the lift. This is like how a car suddenly picks up speed and pushes the head backward for the passenger. This is like the force applied to a spring by a gravitational field. Should the lift speed, the spring would remain stretched, behaving like it was in a gravitational field rather than accelerating. Einstein said these conditions appeared not only similar but exactly the same. Any experiment in an accelerated lift in space would produce the same findings as those carried out in a lift subject under gravity. To finish the picture, consider a lift inside a gravitational field, free to fall within the gravitational field. The spring stops extending when the lift loses all its weight. This is the same in case the lift is at rest, and no gravitational forces are acting. Falling freely, an observer has every cause to assume he is moving inertially. Einstein developed the general theory of relativity armed with this understanding. Still, he would need another 10 years to develop the theory. He had to create a set of guidelines to manage any accelerated motion and gravitational force. He had to learn sophisticated mathematical ideas like Riemannian geometry and tensor analysis to develop a broad formalism to characterize all possible states of motion. He arrived there, though clearly it was difficult. Though technical problems dogged his later work, his classic papers from 1905 distinguished themselves by their great clarity of thought and careful use of mathematical computation. Some say Einstein developed the general theory during his early scientific career. In such a case, he obviously found the procedure difficult. Understanding the nuances of general relativity theory is not easy. The theory seems difficult, even conceptually. Although the general theory combines time relativity with the special theory, gravitational effects cause time dilation and length contraction. Fixing the problems still calls for more solutions. According to the particular theory, space behaves at least satisfactorily. The general theory runs against this claim. Curving is exhibited in the universe. Space warping is so abstract that even physicists struggle to picture it. Greek mathematicians of several generations put great effort into enabling us to comprehend the geometrical characteristics of nature. Among these are the formalized Euclidean theorem, the truth that parallel lines never cross, triangle angles sum to 180 degrees, and many more ideas. Among all these rules, the Euclidean geometry canon is comprised of. Still, these theorems and rules transcend basic abstract mathematics. As experience tells us, they do an amazing job of capturing the characteristics of the physical world. Designers, architects, surveyors, and cartographers who deal with shape qualities and object placement in space know this. Geometry exists there. These spatial characteristics we have known since childhood should transcend the confines of our buildings and study areas. They should be relevant everywhere in the cosmos. Euclid's rules must be included in the world's architecture. Alternatively, must they have? Other guidelines exist for constructing a geometry system apart from Euclid's elegant and logically sound mathematical ideas. Mathematicians of the 19th century, such as Gauss and Riemann, concluded that Euclid's laws were limited to a particular kind of geometry in which space was flat. It is possible to create several systems violating these rules. On a level piece of paper, for instance, sketch a triangle. Euclid's theorems apply here. Thus, the internal angles in this triangle sum up to 180 degrees or 2 right angles. Now, though, consider the results of drawing a triangle on a sphere in its place. On a sphere, one can construct a triangle with 3 right angles. For example, mark 2 points on the equator and 1 on the North Pole, separated by a quarter of the circle. These 3 points challenge Euclidean geometry by forming a triangle with 3 right angles. Although our planet has 3 dimensions of space, this way of thinking is sufficient for 2-dimensional geometry. A curved surface in 3 dimensions is much more difficult to picture. Thinking of space in any one sense is probably inaccurate. After all, space is unbounded. In an astronomical context, rulers, more practically light beams, can determine distances between objects in space. It seems concrete when you picture space as a flat or curved piece of paper. Einstein constantly aimed away from ideas like space, whose existence was dubious. Instead, he considered what an observer in a given experiment would fairly expect to measure. Using this line of research, we can investigate the description of the path taken by light rays in the general theory of relativity. Euclidean geometry has light moving in straight lines. Level environments resemble straight light paths. Special relativity claims that light moves in straight lines and space is flat. Still remember that the broad theory addresses acceleration or motion under gravitational influence. What happens in this case regarding the light? Let us thus go back to the lift thought experiment. Today's lift features a laser beam shining side to side rather than a spring with a weight on the end. Far from any gravitational sources in deep space, the lift is found in the laser equipment, creating the light beam that strikes the side of the lift opposite it, whether it is stationary or moving at a constant speed. This prediction of the special theory of relativity is unique. Imagine, though, that the elevator features a rocket that launches upward on demand. If an observer outside the lift could view the laser beam from outside, he would find that the lift remains straight even as it accelerates away. But a physicist in the lift notes something strange. The light moves quickly from one side of the lift, varying in motion. At the end of its path, the light picks up speed compared to the beginning. This suggests the laser beam strikes the other wall below that side's starting point. An observer within would see the light ray bent downward from acceleration. Consider the equivalency principle in the spring case now. Should the gravitational field match the accelerated lift but lack acceleration? What are the results? Imagine now an elevator situated on the ground of Earth. The light beam must slink downward just as the accelerating lift does. This makes us conclude that light bends under gravity. Moreover, if light paths veer instead of running straight, space becomes curved rather than flat. One reason it's challenging to understand is curved space is not often seen. This follows from the weakness of gravity in daily conditions. Gravity is so weak, even in our solar system, that it generates minimal curvature, and light moves in lines so close to straight that we cannot tell them apart. Newton's laws of motion can fairly depict the events in these situations. We have to be ready for certain conditions, strong gravity and consequences. Newton's gravity fails when a great matter concentration occurs in a small area. Because of how strongly gravity acts, light bends and traps itself when this occurs, warping space. We refer to such an object as a black hole. Laplace also spoke about the existence of black holes in nature, first suggested by English clergyman John Michell in 1783. Still, the most often used connection for these objects is with Einstein's general theory of relativity. One of the first mathematical solutions for Einstein's equations characterizes such an object. Just 1 year after Einstein's theory was published in 1916, Karl Schwarzschild, who died soon after on the Eastern Front during World War I, obtained the solution. Originally meant to form the basis of a mathematical model of a star, this solution corresponds with a spherically symmetric distribution of matter. However, we soon found that the Schwarzschild solution implied that any mass object had a critical radius, now known as the Schwarzschild radius. If a mass is entirely inside its Schwarzschild radius, its surface cannot let light escape. The mass of the Earth is just 1 cm. The Sun's critical radius is almost 3 km. Black holes need compressing matter to an amazing density. Black holes have been extensively studied since Schwarzschild's revolutionary work. Though no clear direct evidence exists, much indirect data suggests that black holes may exist in astronomical objects. An extremely strong gravitational field, roughly 100 million times stronger than the Sun, causes great luminosities in some kinds of galaxies. Recent observational studies on the dynamics of stars near galaxy centers expose high mass concentrations. usually connected with black holes of similar mass, which are the results that are revealed. Nowadays, it is thought that practically every galaxy has a black hole at its center. Black holes with much smaller masses may develop when the energy source of a star fails and the star collapses in on itself toward the end of its life. Although black holes are a topic of great interest nowadays, I will not discuss them in more detail in this book, since they have not been fundamental to cosmology's development. Instead, we will discuss how Einstein's theory clarifies our understanding of universe behavior. Einstein turned out his general theory of relativity in 1915. He began searching right away for means of using this new theoretical framework to explain the vast-scale behavior of the universe. His search for this goal was hampered by his ignorance of the universe he sought to explain. In what actual form did the universe exist? Though he knew little about astronomy, Einstein had to know the answers to a few fundamental questions before advancing. He knew that his ideas could not on their own define the appropriate form and behavior of the universe. This included guesses as well as observations. Unquestionably, thought experiments and pictures help me show the general theory by offering a sophisticated conceptual framework. The brutal truth is that it calls for some of the most challenging mathematics ever applied to explain nature. One can compare Einstein's theory with the more conventional Newtonian approach to grasp the complexity involved. Newton's theory of motion presents only one mathematical equation to solve. F(ma) links the applied force F to an object and its acceleration. Though this equation seems straightforward, this approach can make explaining gravity challenging. The reason all matter in the universe attracts all other matter is found in using this idea to the motion of two interacting bodies, such as the Earth and the Sun, is rather simple. But when more bodies are involved, things get rather difficult. There is no known general solution for any more complicated situation, even though Newton's theory has an exact mathematical solution for two orbiting bodies. This issue still exists, even in three-body counts. Applying Newton's theory to systems with significant collections of gravitating objects is quite difficult, and most of the time, knowledge of what is happening requires advanced computers. The only exceptions are when the system uses a simpler symmetry, such as a sphere, or has uniformly distributed elements over space. Applying Newton's gravity in useful contexts is difficult enough. Einstein's theory poses a formidable obstacle. Unlike Newton's single equation, Einstein's theory consists of 10 simultaneous equations. Moreover, the particular equations are far more complex than Newton's inverse square law. Representing mass as equivalent to energy, the formula E bar mc2 causes all forms of energy to gravitate. An object's gravitational field functions both as energy and a force, often resulting in unmanageable mathematical complexity when solving equations. This issue, which physicists call non-linearity, often causes. This is also true of general relativity. There are rather few exact mathematical solutions to Einstein's equations. Even with special symmetry, the theory presents major difficulties for computers and mathematicians. Einstein knew his equations would be difficult to solve, thus his best bet of success would be to assume that the universe displayed some homogeneity or simplifying symmetry. The contents of the universe still remained totally unknown in 1915. Many astronomers saw the Milky Way as an island universe, while others believed it was only one of several such objects strewn roughly equally over space. The later choice especially piqued Einstein's curiosity. It would be difficult to sufficiently explain this ugly slab of gas, dust, and stars if the Milky Way were the whole universe. The second option was better, and allowed a rough and ready description whereby the Milky Way and other galaxies were the fine details in a generally smooth distribution of material. Mach's principle offered a philosophical justification for Einstein's inclination toward great smoothness. Should all in the universe be the same? He could build a strong basis for his cosmological theory by letting matter distribution define a unique reference frame that would help control the consequences of gravity. Einstein homogenized his universe even without much observational evidence. He also thought the universe was isotropic, that it looked the same in all directions. The cosmological principle is derived from these two underlying presumptions. Although related, the twin presumptions of homogeneity and isotropy cannot be switched. Isotropy does not always indicate homogeneity if one does not assume the observer is in a unique position. Only in the center of a distribution of matter with spherical symmetry could there be isotropy. An observer seated in the middle of a circular carpet with a concentric ring pattern would only see the carpet as isotropic. A clue to the debt modern cosmology owes to the past is the Copernican principle, which holds that people do not live in a special place in the universe. Observed isotropy and the Copernican principle indirectly imply the cosmological principle. The Milky Way is obviously not isotropic. Anyone who has looked up at the night sky will know. It moves clearly in a band across the heavens. A universe comprising the Milky Way alone could not follow the cosmological principle. The outstanding-sounding name cosmological principle should not mislead one about its origin. We usually introduce ideas to progress when we need more data. In cosmology, this also applied. This estimate was quite accurate. The nebulae were discovered outside the Milky Way in the 1920s. More recent observations of the cosmic microwave background and the broad-scale distribution of galaxies support the theory that the universe is smooth at big distances. Only recently have astrophysicists created a strong case for the unique symmetry of the universe. Cosmic inflation addresses the horizon problem, the mystery source of great smoothness. Equipped with the cosmological principle, Einstein generated logical mathematical models of the universe. Still, he ran across a problem right away. Based on cosmological ideas, his theory mandated dynamic spacetime for every solution to his equations. He could not build a model of a fixed, unchangeable universe across time. His thesis said the universe had to expand or shrink, but it did not indicate which of the two possibilities would be accurate. Einstein sought experts on the movements of far-off stars, even though he had little knowledge of astronomy. He got the reply that, generally speaking, the stars were neither moving closer to nor farther away from the sun, probably because he asked the wrong question. While we know this is untrue for other galaxies, it is true within our own galaxy. Knowing the universe should be stationary, Einstein went back to his original equations. He realized he could retain their fundamental character while making a minor change to counter the tendency of his cosmological models to expand or shrink with time. He modified the theory by introducing a new term called the cosmological constant, which indicates a change in the behavior of gravity at the biggest sizes. The theory modulates the cosmological constant to balance the expansion or contraction the universe would naturally experience. Temporarily happy with this answer, Einstein developed a stationary cosmological model and published it in 1917. A few years later, in 1929, Hubble published his results, which helped to realize the universe was expanding rather than stationary. Einstein's original model is historical nowadays. He introduced the cosmological constant without trouble, even without stopping world expansion. Einstein, later on in life, said that this episode was the largest error he had ever committed in his scientific career. Though most people interpret this as a reference to the cosmological constant, the mistake was not foreseeing the universe's expansion. Though most cosmologists were happy to exclude it from their models, the cosmological constant has never disappeared until recently. Always lurking in the background, it was like a crazy relative living in an attic. We will show how it has come out of obscurity and taken front stage again. Not all scientists, including Einstein, shipped their attention to cosmology once the general theory of relativity was published in 1915. Alexander Friedmann was a little-known Russian physicist and otherwise. Not Einstein, but Friedmann developed the mathematical models of an expanding universe that supported modern Big Bang cosmology. His achievements are remarkable since he finished his calculations under great difficulty during the Petrograd siege. Friedmann died in 1925 before his 1922 published work gained recognition abroad. Later on, Stalin closed the institute where Friedmann had been working. A Belgian priest called Georges Lemaitre independently produced the same results at some point later, which spurred Western European academics to look at and promote these ideas. Assuming that there is no cosmological constant and demanding that the cosmological principle is true will help you to obtain the simplest Friedmann models, a special collection of solutions to Einstein's equations. The cosmological principle is a fundamental component in several models. Under relativity theory, space and time are relative ideas. Generally speaking, Einstein's theory must offer a clear way to differentiate between space and time. We mathematically describe the when and where of an event in terms of a complex, conceptually difficult four-dimensional space-time. Different observers would disagree about the time between events depending on their motion and the gravitational fields they have come across. Applying the cosmological principle and creatively considering time helps one to simplify everything. The mass of a clock depends on its matter content. Since the density of a homogeneous universe has to be constant everywhere, as the universe expands, the space separating particles increases and reduces the density of matter. Matter's density drops with time. Higher densities also imply an earlier time. Perfect synchronizing results are obtained when observers set their clocks depending on the local density of matter anywhere in the universe. Perfect synchronization is thus achievable. We call the resultant measure of time cosmological proper time. Since density is constant everywhere, the cosmological principle helps to further simplify how space might curve in response to gravity. Through the Einstein equations, the density of matter and/or energy controls the curvature of space. Though we have to do it consistently, space can be bent. 3 different situations exist whereby this could take place. The most clear approach to guarantee consistency is to have no curvature. Sometimes people call this the flat universe. Euclidean geometry's rules apply in a flat universe where light moves in straight lines exactly as in the normal universe. But if space stays uncurved, what relevance does gravity then have? Given the flat universe, why does it matter about warp space? The mass warps of the universe balance its expansion. Matter and energy cooperate to oppose each other's gravitational attraction. Time stays curved even in cases of a flat space. The flat universe is special since it requires a careful equilibrium between the gravitational pull of matter and expansion. Should the expansion of matter and the gravitational pull be out of balance, 2 possible results follow. A high density of matter in the universe results in a stronger gravitational pull from which space contracts inward, mimicking the surface of a sphere in 3 dimensions. In mathematics, under such conditions, space has a positive curvature. In this sense, light beams in the closed universe really converge on one another. Whereas a flat universe can span endlessly in all directions, a closed universe has a finite size. Return one direction from your beginning. Another choice is the open universe. This is also infinite. But the negative space curvature makes the view more challenging than in the closed form. These models' space behavior reminds one of the evolution of time. Apart from their limited length, closed universes are finite spaces. It will finally slow down if the universe keeps expanding and remaining closed. At last, the universe will stop growing and collapse once more. Flat and open models will always expand. In the Friedman models, gravity always resists the universe's expansion. Only in the closed model does it triumph. Friedman's models form the foundation of most Big Bang theories and reveal their main mistakes. They use these computations to stop its expansion and bring it back to its starting condition. The earlier we travel, the denser the universe becomes. In mathematics, a singularity results from trying to go too far back. In mathematics, a singularity is a pathological quality whereby, during a computation, the numerical value of a given quantity becomes infinite. For a simplified illustration, let us determine the Newtonian force acting on another particle from a large body resulting from gravity. Since this force is inversely proportional to the square of the distance between the two bodies, the result would be infinite if one tried to calculate the force for objects at zero separation. Sometimes the only clue of major mathematical problems is singularity. Sometimes their outcome is a result of poor coordinated choice. For example, the standard maps of an atlas exhibit anomalies akin to those of singularities. These maps seem sensible unless you study them closely. Rather than presenting the North Pole as a point, the standard equatorial projection shows it as a straight line from a point along the top of the map. One would find nothing sinister on a trip to the North Pole. The coordinate singularity of this point can be changed to give it a further impression of distance. Trying to cross this singularity won't cause you anything particularly unusual. The solutions of the general relativity equations show shockingly often occurring singularities. Among them are coordinate singularities like the one I described. Their seriousness is not very great. But what distinguishes Einstein's theory is that it predicts the existence of actual singularities, that is, circumstances whereby real physical quantities such as temperature or matter density become infinite. Under certain conditions, the curvature of space-time can become infinite. Many feel that the existence of these singularities causes some basic physics, explaining the gravitational effect of matter at extreme densities to be missing. Using a quantum gravity theory, scientists could calculate what happens far within a black hole without presuming that all mathematical quantities are infinite. Actually, in 1950, Einstein himself wrote, "The theory is based on separating the concepts of matter and gravitational field. This is a reasonable approximation for weak fields, but is likely insufficient for very high matter densities. Consequently, one should not assume that the equations apply for very high densities, and a singularity in a unified theory might not exist." The most famous example of a singularity in a black hole is in its center. The original Schwarzschild solution features this hole with perfect spherical symmetry. For many years, physicists thought that the only cause of a singularity of this sort was this spherical solution's rather artificial special character. However, in several studies, Roger Penrose and associates have shown mathematically that singularities arise whenever objects fall under their own gravity, suggesting that special symmetry is superfluous. General relativity seeks to conceal these singularities as an apology for predicting them. An event horizon encircling a Schwarzschild black hole keeps outside observers from view of the singularity. Thus, general relativity most likely shields all singularities, and naked singularities are not regarded as physically realistic. But Stephen Hawking thought he might try applying Roger Penrose's 1960s mathematical analysis of the black hole singularity in other settings. Penrose imagined a time when something would give in to gravitational power. Hawking wanted to find out whether he could use these ideas to explain the expanding past events of the universe. Following talks on this with Roger Penrose, Hawking worked with him on the now famous cosmological singularity. Collectively, they showed how expanding universe models demand the presence of an initial singularity whereby density and temperature approach infinite values. Notwithstanding all else, the universe's openness, closedness, or flatness determines a basic limit to our understanding. At first, there was infinite. Most cosmologists agree that Einstein's equations broke down at some point due to the extreme physical conditions of the early universe, much like the black hole singularity already covered here. This is their interpretation of the Big Bang singularity. If accurate, the only approach to understanding the first phases of the universe's expansion is to create a more advanced theory. We lack one, so the Big Bang theory is inadequate. Specifically, we must know the total energy budget of the universe to ascertain whether it is closed or open. Thus, theory alone cannot tell which of these alternatives is the correct description. This imperfection makes the term model more suitable for the Big Bang than theory. Some basic questions, such as whether the universe will expand indefinitely due to their ignorance of its initial conditions, still need definite responses from cosmologists. My main focus has been on how developments in theoretical physics, especially the general theory of relativity, shaped important changes in cosmological theory during the 1920s. These new ideas, however, were only generally embraced once improved observational instruments. Let astronomers begin precisely calculating the motions and distances of galaxies. These observations and their connection to the theoretical framework will be discussed in this movie. A single, simple equation, the Hubble law, explains the features of the universe's expansion. This means a galaxy's apparent speed, v, is proportional to its distance, d, from the observer. Originally known as the Hubble constant, denoted by the letters h or ho, the constant of proportionality is now. We thus write the Hubble law as v hod. The relationship between v and d is linear since, as Hubble did, the measured velocities and distances of a sample of galaxies plot a straight line. Ho sloppiness characterizes this line. The Hubble law holds that galaxies travel away twice as fast when their distance from the observer doubles. 3 times farther away, galaxies move at 3 times their speed, and so on. Hubble published his well-known law in 1929 following spectra analysis of a galaxy sample. American astronomer Vesto Slipher also deserves a great share of the credit for the discovery. Despite his imprecise distance estimates, Slipher obtained spectra of a group of nebulae, as galaxies were then known, that displayed this relationship as early as 1914. Sadly, Slipher never published his initial results, which he presented at the American Astronomical Association's 17th meeting in 1914, and his contribution has never gotten the due credit from history. How, then, did Hubble arrive to have his law? He applied spectroscopy as his method. The light of a galaxy comes from the range of colors created by all of its stars. A spectroscope can split light into separate hues to independently study its exact color mix. Using a prism will help one easily reach the same objective. Normal white light can be split by a prism into a rainbow-like spectrum. Still, astronomical spectra exhibit unique colors and pointed features called emission lines. As an object moves between several energy levels, electrons within its gas form these lines. Depending on the source's chemistry, laboratory studies can exactly track these transitions at designated wavelengths. Many of Hubble's galaxies showed clearly detectable emission lines, but he discovered that in the measured spectrum they typically fell in the wrong place relative to the lines. Near always, they caused the lines to move toward the red end of the spectrum toward longer wavelengths. Hubble noted this as a Doppler change. In the 1840s, physics welcomed the Doppler effect with great fervor. This is true since the first experimental proof of this effect used several trumpeters on a steam train. The main emphasis of this application was the generated sound waves when the source and receiver moved about one another. The effect is well known from daily life. A police siren approaching sounds louder than one receiving. The easiest approach to grasp the influence is realizing that sound pitch is determined by wavelength. High pitch points to a small wavelength. Approaching the speed of sound, a source's apparent wavelength reduces since it usually catches up with the waves it generates initially. Its apparent pitch lowers because of the widening gap between it and the waves it generates behind it, as it also tends to surge ahead of it. In an astronomical context, light experiences the Doppler effect. Usually small, the effect is only apparent when the velocity of a source matches a significant fraction of light's speed. Unless the car moves rather fast, the Doppler effect for sound stays small. The relevant scale depends on the sound speed. An emission source typically emits a shorter wavelength approaching the observer and a longer wavelength away from it as it moves. Under these circumstances, the light moves to the red and blue areas of the spectrum, respectively. Stated differently, a red shift indicates a receding source. A blue shift indicates an approaching source. But if the source emitted white light, no change would be evident. Assume X to be the wavelength redshift of every line. We would next see the light at wavelength Y plus X. Still, we would see the same quantity of light at the original wavelength. Why? Since the light first emitted at wavelength YX would move there to fill the void. Doppler shift or not, white light still looks white. One must see an effect by observing emission lines at discrete frequencies. Thus, no such compensation is possible. In the laboratory, it is easy to determine the degree of shift of a set of lines around a stationary source, since the spectrum will shift an entire set of lines in one direction or another, maintaining their relative spacing. Hubble's redshift indicated more distant galaxies than the surrounding galaxies in his sample. Assuming he saw a Doppler shift, he converted the changing spectral lines into a velocity measurement. He derived his famous linear relationship by plotting this apparent recession velocity against the distance. Though he now understands Hubble's law, Hubble never concluded that the universe is expanding. Lemaitre most likely first proposed Hubble's law in terms of the universe's expansion overall. Though it anticipated Hubble's seminal paper of 1929, Lemaitre's 1927 paper had minimal impact due to its French writing and publication in a little-known Belgian journal. Thanks in part to British astronomer Arthur Stanley Eddington, the more eminent monthly notices of the Royal Astronomical Society did not publish Lemaitre's paper in English until 1931. One of the main foundations of the Big Bang theory is the identification of the Hubble law with cosmic expansion. Thus, Lemaitre deserves respect for having made this essential action. Galaxies seen moving away from us point to us as the center of the expansion. This violates the Copernican principle and marks us in a unique position. One answers, no. Any other observer would likewise see everything fading. Regarding the expansion, every point in the universe is equal. Mathematical evidence also supports applying Hubble's law in a universe expanding uniformly and isotropically, which conforms with the cosmological principle. The universe cannot expand except in this way. Visualizing the scenario would be easier if one reduced the 3 dimensions of space to the 2-dimensional surface of a balloon, which would represent a closed universe. But for the purposes of this illustration, the geometry is not especially important. Apply dots to the balloon, then inflate it. Every dot watches the others fade as if it were the center of expansion. However, the flaw in this analogy is that our ordinary 3-dimensional space embeds the 2-dimensional surface. As such, people view the space inside the balloon as the real center of expansion. False is this. One has to regard the balloon as the whole universe. The balloon exists in no global center in another space. Every point in the balloon represents its center. This issue usually requires an explanation of the location of the Big Bang. Are we moving further from the explosion site? Where was this explosion located? The theory is that everything moved away from the everywhere occurring explosion. Everything stayed the same while the Big Bang singularity started. The Hubble law still presents some interpretation difficulties even more than 70 years ago when Lemaitre discovered it. Hubble measured redshifts only. Velocities had not been measured. In cosmology, the redshift is usually denoted by the symbol z, which denotes the fractional change in wavelength concerning the expected position of an observed line. Hubble's law sometimes relates redshift z to distance d, rather than a straight relationship between recession, speed, v, and d. In this case, the redshift is roughly the velocity of the sources stated as a fraction of the speed of light. Hence, there is no problem if the velocities in the issue are much smaller than the speed of light, c. If z, d, and z and v are equal, v and d must be proportionate. However, at large redshifts, this link breaks down. Which shape would then be suitable? In the Friedmann models, Hubble's law is remarkably easily interpreted. The recession velocity v and distance d have an exactly linear relationship even at arbitrarily high velocities. Learning that objects cannot travel faster than light could cause some people concern. Distance in a Friedmann universe accelerates an object's velocity away from the observer. The object's velocity can be selected to surpass the speed of light. However, this does not go against relativity, since the observer cannot see the infinite redshift. Its measuring and definition could also need changes. Usually, astronomers cannot accurately ascertain an object's distance most of the time. Usually too great to use triangulation like surveyors, the distances involved can span a ruler to a far-off galaxy. Instead, they have to gauge the object with the light it produces. Objects are no longer in the same places since Hubble found the universe is expanding and light travels only at a limited speed. Astronomers, thus, must consider the universe's expansion and locate the object through indirect distance measurements. Still, the theory has some value in this situation as well. One can easily consider source velocities and distances. Though most people know the redshift as a Doppler shift, a more direct and exact approach exists to see this effect. In the expanding universe, the distances separating points develop uniformly in all directions. Think about an expanding graph paper sheet. Eventually, the conventional grid on paper will resemble an enlarged form of its past look. Maintaining symmetry will help us to retrieve the earlier grid by determining the reason behind the later grid expansion. Similarly, you only need to know an overall scale factor to use data from the present to determine the physical conditions in the past. A uniform and isotropic universe does not change as it expands. Commonly expressed as the symbol AT, this element aligns with the Friedmann equations. Remember that the finite lifetime of light is what drives everything. Light from a far-off source arriving now has to have begun at a particular point in the past. Having expanded, the universe was smaller and younger at the time of emission. The universe's expansion would stretch the light waves emitted across space by the same quantity between their emission and their detection at a telescope. For a universe expanded by a factor of 3, the wavelength would triple, for example. The observed redshift of the source is thus 2, a 200% increase. Should the expansion factor be 10%, 1.1, etc., the redshift would be 0.1, 1.1, etc. Due to cosmological expansion, space-time stretches produce a redshift. Physicists haven't arrived at this clear interpretation for many years. 1917, Wilhelm de Sitter produced a cosmological model predicting redshift for light rays. He was unsure his model reflected an expanding universe, since he had stated his results using unusual coordinates. Instead, he sought to understand what he had found to be some unusual gravitational influence. Although the de Sitter effect remained poorly known for many years, we know it to be quite simple today. Furthermore, not everyone must take part in the growth. We exclude items held together by forces other than gravity. This covers atoms, molecules, rocks, and elementary particles. Rather, these don't expand with the universe, they stay a constant physical size. Similar to this, objects with a strong gravitational field oppose expansion. Gravity holds planets, stars, and galaxies so tightly that they cannot expand with the rest of the universe. Not all objects are moving apart on scales larger than galaxies. For instance, due to their mutual gravitational attraction, the Milky Way and the Andromeda Galaxy, M31, are getting closer to one another. The cosmic flow also holds certain massive galaxy clusters together. Unlike individual galaxies, greater objects might not always be bound, but their gravity might still be potent enough to distort Hubble's law. At large distances, we have established the linearity of the Hubble law, yet a significant scattering exists around the straight line. However, statistical errors and uncertainties in the distance measurements contribute to the incomplete picture. Only objects moving in an idealized, homogeneous, isotropic universe satisfy Hubble's law precisely. Our universe might resemble this on sufficiently large scales, but it is not uniform. The scatter in Hubble's plot is caused by its clumpiness, which deflects galaxies from the pure Hubble flow. On the largest scale, however, no force can counteract the universe's inherent inclination to expand over time. Hubble's law ignores all these rather minor perturbations and characterizes the accelerating separation of matter from matter. I have focused on theoretical interpretation and framework of the Hubble law. We also have to take into account the importance of another essential component of Hubble's law, the constant Ho. One of the most important numbers in cosmology, the Hubble constant Ho, also reflects shortcomings of the Big Bang model. Our theory breaks down and cannot forecast what value it should have, thus this great number is part of the information imprinted at the beginning of the universe. Finding Ho's actual value from data is difficult. Astronomers need two measurements, first revealing the galaxy's redshift. Spectroscopic studies establish its velocity. You can finish this section quite quickly. Doing the second measurement, that of distance, is much more difficult. Imagine yourself in a large, pitch-black room with a bulb placed at any distance from you. You will measure the distance how? One would want to try some triangulation. Using a theodolite surveying tool, you could sweep the room, mark angles to the flashlight from different points, then use trigonometry to determine the distance. Another approach is measuring distances by applying the properties of the light the bulb produces. Assume for the moment that you knew the bulb was a 100-watt model. Just visualize also a light meter. Remember that light intensity falls with the squared distance. Thus, you could find the distance to the light bulb by measuring the amount of light you get using a light meter. This technique only works, though, when the power of the bulb is known. If the wattages of two identical bulbs in the room were the same but unknown, you could then rapidly ascertain their relative distances. For instance, the first bulb has to be twice as far away as the second if its reading on your light meter is 4 times smaller than that of the other bulb. You still must, however, precisely determine the distance to every bulb. Transposing these concepts into an astronomical framework emphasizes the difficulties in establishing the distance scale of the universe. Triangulation is complicated since, absent some conditions, it is impossible to move noticeably over the involved distances. See below. Measuring absolute distances to stars or other sources is also easier until we ascertain their inherent luminosity or power output. Stars cannot be resolved even with the most strong telescopes, thus a faint star near seems to be a massive star far away. Calculating relative distances gets easier, though, if we know two stars or other sources are identical. On the extragalactic distance scale, calibrating these relative distance measurements is the main chorea. To put these difficulties into perspective, our understanding of the scale of the universe was still rather poor in the 1920s. Before Hubble's discovery, most people thought the universe was quite small. The spiral nebulae, then known as, were thought to exist outside of the Milky Way. Usually these nebulae, now known as spiral galaxies like the Milky Way, were thought to reflect the first phases of building structures akin to our solar system. Hubble computed the value of Ho, the Hubble constant, usually expressed in megaparsecs or 500 km/s, when he revealed the finding of his namesake law. This is roughly 8 times greater than present projections. Baade corrected Hubble's error in choosing which type of star to use as a distance indicator in the 1950s, see below, so reducing the value to almost 250 in the same units. Sandage changed the value once more in 1958, putting it between 50 and 100. Current observational estimates still lie in this range. Modern Ho measurements make use of a spectrum of increasing scale distance indicators. Starting with approximations of the distances from surrounding Milky Way stars, they finish with the farthest galaxies and clusters. Still, the fundamental idea is the same as it was when Hubble and Sandage first put it forth, so underscoring the consistency of scientific methods. We first derived the scale of the Milky Way from local kinematic distance observations. Though they do not call for knowledge of a source's absolute luminosity, kinematic approaches resemble the previously mentioned idea of triangulation. First, the trigonometric parallax of a star allows us to determine the distances to rather close stars, so expressing the star's position in the sky in a year due of Earth's motion in space. The parsec, PC, that this approach produced became the accepted astronomical unit of distance. 1 parsec away, star produces a parallax of 1 second of arc when the Earth moves from one side of the Sun to the other. 1 parsec stands for about 3 light years. A major astrometric satellite, Hipparcos, measured the parallax of thousands of stars in our galaxy. Another important group of distance indicators are variable stars. The most important ones are the Cepheid variables. Variability of these objects reveals their inherent luminosity. The absolute luminosity, L, and period of variation, P, show a close relationship among the brilliant variable stars sometimes referred to as the classical Cepheids. Thus, by determining the P of a far-off Cepheid, we may approximate its L and distance. These stars' luminosity helps them to be seen in galaxies far beyond our own, so extending the distance scale to almost 4 MPC, 4,000,000 PC. Errors in the Cepheid distance scale brought on by galactic rotation, interstellar absorption, and mixing of the Cepheids with the W Virginis variables, a different group of variable stars, mean Hubble's first estimate for Ho much too high. A modest ladder extension of roughly 10 MPC is made possible by extrastellar distance markers. We consider these methods as main distance indicators taken together. HII regions, vast clouds of ionized hydrogen encircling very hot stars, and globular clusters, groups of roughly 100,000 to 10,000 stars, are secondary distance indicators. For these objects, the former exhibits an absolute luminosity and a modest scatter around the mean. Main approaches calibrate such relative indicators, so extending the distance ladder to almost 100 MPC. Among the tertiary distance signals are the brightest cluster galaxies and supernovae. Up to 1,000 galaxies can be found in one single cluster. The brightest elliptical galaxy in a rich cluster most likely developed by consuming other galaxies, hence their standard total luminosity is rather low. Hundreds of millions of light-years separate the brightest galaxies. Supernovae are star explosions releasing light roughly equal to a whole galaxy. These stars thus are quite obvious in far-off galaxies. Researchers have also investigated many other indirect distance approximations, including relationships between several inherent features of galaxies. Ho can thus be found using many different approaches. Why, then, is knowledge on Ho's value still so much needed? We have to make corrections at every level, since even a small mistake on one rung of the distance ladder can have cumulative effects on next levels. Rotation of the galaxy affects the Milky Way. Changes in telescope aperture. Milky Way is affected by absorption and obscuration, various forms of observation-related biases. Given a lot of doubtful corrections, it is not surprising that we can still ascertain Ho with remarkable accuracy. The distance scale has been dominated by controversy ever since Hubble's time. Still, given the most recent technological developments, a solution to this conflict seems just around the horizon. We expect the key program of the Hubble Space Telescope, HST, to fix Hubble's constant value to approximately 10% on the distance scale, so eliminating the main sources of error in the calibration of conventional steps in the distance ladder. We can take images of stars, especially Cepheid variables, directly in galaxies in the Virgo cluster of galaxies. The most current estimates, derived from an inadequate program, fall on a Ho value of 60-70 km/s per megaparsec. From the Hubble constant, it would be rather easy to ascertain the age of the universe if it grew at a constant rate. Despite their distance now, all galaxies had to start together. We just need to calculate when the universe happened to ascertain its age. The age of the universe can be computed readily from the inverse of the Hubble constant. The age of the universe is, roughly speaking, 15 billion years. But this computation would only be valid in an empty universe free of any element able to stop the expansion. The Friedmann model slows down the evolution based on the mass of the universe. Although the exact deceleration needed is yet unknown, the age will always be less than past calculations. A slowing expansion suggests that the universe expanded and passed faster speed. Still, the effects of slowing down are not really significant. 10 billion years old should be a flat universe. One independent approach to find the age of objects in the universe is dating them. Since the Big Bang originates all matter and space-time, clearly nothing in the universe should be older than the universe. It is challenging, though, dating astronomical objects. By means of radioactive decay of long-lived isotopes, such uranium-235, whose half-life spans billions of years, terrestrial rocks can ascertain their age. The solar system is the only source of elements with far longer half-lives than carbon. 14. In archaeology, this method differs from radiocarbon dating primarily in that it must be applied over a far longer period of time. Although lunar and meteoritic rocks are older than terrestrial material, their formation may have happened rather recently in the history of the universe. Hence, they are useless in a cosmological perspective. The most efficient, less direct methods of ascertaining the age of the universe are: the strongest limits of the studies on worldwide star clusters are related to most of the stars in these clusters have low masses. Thus we suppose they formed all at once. We can ascertain the evolutionary background of these stars since they all developed concurrently. The projected age of the universe is smaller since the formation of the clusters first requires some time following the Big Bang. Though this has lately come under criticism, recent studies indicate that such systems may be about 14 billion years old. This directly challenges the hypothesis about the flat universe. The brief lifetime of such universe cannot allow the age of globular cluster stars. This case holds that we live in an open universe. The ancient star ages, which also more recently and significantly coincide with other data, imply that the universe is expanding rather than contracting. Though the basic theoretical framework of the Friedman models has existed for a long period, the Big Bang theory has only lately emerged as the most likely general explanation for the changes in the contents of the universe. The alternative most cosmologists have long preferred is the steady-state model. The Big Bang itself really took several forms. To set the modern theory apart from an earlier competitor now abandoned with a cold, initial phase, we more precisely refer to it as the hot Big Bang. Calling this a theory is untrue, as I said. A theory and a model differ in rather small ways. Still, generally speaking, one expects a theory to be fully self-contained. That is, to have no adjustable parameters and an a priori definition of all mathematical quantities, while a model lacks these qualities. The uncertain early phases of the Big Bang make accurate forecasts about it challenging, which makes testing challenging as well. One of the criticisms leveled most often by supporters of the steady-state theory is, surprisingly, one of the most well-known detractors of the model, Sir Fred Hoyle, initially planned Best's Big Bang to be negative in a BBC radio program. According to the steady-state cosmological model put forth by Gould, Hoyle, Bondi, and Narlikar, the universe has constant characteristics even in expansion, based on the perfect cosmology theory, which is based on a more general form of the cosmological principle, this theory. Like it is in space, the universe is homogeneous and isotropic in time, according to it. Every quality of steady-state cosmology has to stay the same across time. There is a solution for this equation found in the Einstein equations. We term this the de Sitter solution. Nevertheless, if the universe is expanding, the density of matter has to drop with time. Is it imperative? According to the steady-state theory, the C field generates matter constantly to offset the dilution brought about by cosmic expansion. This theory is valid even in the absence of direct lab observations. We have not seen this continuous creation process in the lab. Nevertheless, the small rate of creation required, about 1 hydrogen atom per cubic meter in the age of the universe, makes it difficult to exclude it as a plausible physical process. Since testing it proved simpler, more especially, any evidence implying a different universe would challenge the theory. Beginning in the late 1940s, researchers sought for variations between the characteristics of nearby and distant galaxies, which one would consider as historical. The difficulty of such observations and interpretation problems led to acrimonious conflicts between the supporters of the steady-state theory and its opponent. One such conflict concerned radio astronomers Martin Ryle and Fred Hoyle, who asserted to have found notable change in radio source characteristics. An inadvertent discovery in the middle of the 1960s resulted in the independent and critical resolution of the argument. Early in the 1960s, two physicists, Arno Penzias and Robert Wilson, investigated emissions from Earth's atmosphere using an odd microwave antenna fashioned like a horn, left over from testing communication satellites. Investigating possible interference sources that might compromise future satellite communication plans was the design aim of the telescope. Penzias and Wilson were amazed by the continual background noise. Before they understood the noise would never go away, they spent much time searching and removing pigeon nests from their telescope. Dickey and Peebles thus happened to be members of a group of astrophysicists attempting to set up an experiment in Princeton, New Jersey, in search of evidence of Big Bang radioactivity. They began to accept their loss in the race. Published in the Astrophysical Journal in 1965, the Dickey Group's paper clarifies the importance of Penzias and Wilson's finding. Penzias and Wilson were Nobel Prize winners in 1978. Extensive studies conducted since 1965 have helped us to grasp the microwave background. Penzias and Wilson discovered, against atmospheric theory, that their noise was independent of the time of day. Actually, the very high homogeneity of the microwave background radiation points to the fact that it is not connected to sources in our galaxy that would not distribute consistently over the sky. Unquestionably, the background is extragalactic in character. Importantly, for this radiation we have defined a particular spectrum called a black body. Black body spectra follow from a perfect radiation emitter and an ideal radiation absorber as the source. We sometimes refer to the radiation produced by a black body as thermal radiation, since its perfect absorption and emission bring the source and the radiation into thermal equilibrium. The unique blackbody spectrum of this radiation amply shows that it started in early stages of the primordial fireball under thermal equilibrium conditions. Now in the microwave background, it is less than 3 degrees above absolute zero. But this radiation has been gradually cooling as the universe expands and every component photon undergoes a redshift. Turning back the development of the universe to earlier eras results in hotter and more energetic photons. At last, the radiation reaches a point where it starts to fundamentally alter matter. In a normal gas atom, electrons circle nuclei, but a strong radiation field strips away the electrons, producing a plasma that ionizes the material. This would have happened some 300,000 years following the Big Bang, when the universe was almost 1 billion times denser and 1,000 times smaller than it is today, and temperatures were several thousand degrees. At this time, the Sun's surface, which also radiates in near-black body form, was the same temperature as the whole universe. Rapid collisions between radiation and matter, especially free electrons which maintain thermal equilibrium, follow from complete ionization. Ionization thus renders the universe dark to light. As it cools and expands, the electrons and nuclei recombine into atoms. Photon scattering is much less efficient when it happens. The cool remnant radiation we observe today comes from electrons during the recombination epoch. Electrons and nuclei combine into atoms as they cool and expand following recombination. When first emitted from scattering processes, this radiation fell in the optical or UV spectrum. The universe's expansion has progressively redshifted it, exposing it at infrared and microwave wavelengths. But this has been revealed gradually. These hints, though, pale in importance to the Big Bang theory. Cosmologists can deduce conditions from the microwave background during the Big Bang, so clarifying the chemistry of the universe. The universe consists of quite simple molecules. The most well-known cosmic material is hydrogen, the most fundamental chemical component having a single proton nucleus. More than 75% of the universe consists in simple matter. Apart from hydrogen, helium-4, a stable isotope of helium with 2 protons and 2 neutrons in its nucleus, makes up around 25% of the material components of the universe by mass. Comparatively to 2 other exotic elements, this is almost 100,000 times rarer. The nucleus of deuterium, sometimes known as heavy hydrogen, is 1 proton plus 1 neutron. The lighter isotope of helium, helium-3, has 1 neutron less than its heavier relative. Our produced last trace element is lithium-7, a 10 billion hydrogen atom component. How did we formulate this chemical combination? Stars have been known to function by burning hydrogen, a kind of nuclear fuel since the 1930s. Stars synthesize helium and other elements during this process. Stars cannot, however, produce the mixture of light elements I just described. Strong radiation of stars. How did we mix these compounds? More rapidly than they can synthesize, the chemicals break down into protons and neutrons, though the ease with which stellar interiors generate heavier elements than helium-4, the observed percentage of helium-4 defies conventional stellar evolution predictions. Alpher, Bethe, and Gamow knew early on in the 1940s that it would be challenging to explain helium abundance just from the ease with which stellar interiors generate heavier elements than helium-4. The observed percentage of helium-4 defies accepted predictions of stellar evolution. Calculating the relative concentrations of light nuclei produced in the primordial fireball calls for some presumptions regarding the nature of the universe at that time in its history. O-synthesis era in 1948. Alpher and Hermann calculated that this background should be 5K, quite near to a known temperature. Still, determining the cosmic microwave background radiation would take roughly 15 years. We have to pay attention to its relevant phase of development. Apart from the usual presumptions made in the Friedmann models, one must assume that the early universe experienced a phase of thermal equilibrium at temperatures above 1 billion degrees. Before nucleosynthesis starts, this would have weak nuclear interactions continuously transform protons and neutrons. More on these nuclear interactions later. Starting model of Bang. Apart from that, rather basic computer codes meant to replicate thermonuclear explosions can handle the computations. These nuclear interactions later. If protons and neutrons are in thermal equilibrium, we can figure their relative counts. The fast, weak interactions in the meantime allow the neutron-proton ratio to constantly change to fit the cooling surroundings. But at a certain critical point, the weak nuclear reactions lose their efficiency and the ratio turns insensitive. The ratio freezes out, that is, roughly 1 neutron for every 6 protons, once it reaches a specific point. Mostly this ratio controls the ultimate helium-4 abundance. Create deuterium first, then add protons and neutrons to form helium. As I said already, radiation easily disturbs deuterium. When a photon runs across a deuterium nucleus, it splits into a proton and a neutron. Furthermore, the neutrons that froze out earlier start to decay around 10 minutes. We call this the bottleneck for deuterium. This nuclear traffic congestion hinders helium synthesis. Besides, the neutrons that froze out earlier decay in about 10 minutes. After the delay, neutrons available for cooking helium somewhat decrease. Remains present for long enough to induce further reactions and is insufficient to separate deuterium when the radiation bath's temperature falls below 1 billion degrees. These two reactions happen rapidly during welding, transforming almost all neutrons into helium-4 and leaving small amounts of deuterium and helium-3 behind. The reactions generate just trace levels of intermediate deuterium and helium-3. By mass, the needed abundance of naturally occurring helium-4 is about 25%. Furthermore, quite nicely in line with the observations are the intermediate nuclei quantities. The primordial fireball does all these chores in the first minutes. Regarding the theory, which is essentially this is an amazing success. But the baryon to photon ratio of the universe limits the agreement between exact calculations of the nuclear fallout of the Big Bang and the discovered elemental concentrations. The number only serves as whole when it is roughly 1 in 10 billion. One proton or neutron exists for every 10 billions of photons. We can determine the total photon count in the universe using the known temperature of the microwave background. This is quite accurate for what we need. We can find the baryon count using the suitable value since we know the baryon to photon ratio required for nucleosynthesis to operate. The result is hardly noticeable. There is only a small fraction of the mass required to close the universe existing as baryonic matter. Two of the main successes of the Big Bang theory are synthesis of elements during the nuclear fireball and generation of the microwave background during the recombination period. How closely observations match complex computations supports the model. Inspired by these successes, cosmologists have used the Big Bang theory to probe further effects of matter at very high densities and temperatures. In this exercise, the Big Bang exploits the link between large and small. Further back in time, the universe gets smaller and hotter. Our epoch comes roughly 15 billion years following the Big Bang. We formed the microwave background almost 300,000 years ago following the Big Bang. Within the first minutes, the nuclear furnace finished cooking. Propelling our knowledge of the universe backwards in time depends on an awareness of the behavior of matter at energies above those attained in nuclear reactors. We can only create highly expensive experiments able to probe such amazing energy scales. Although some characteristics of primordial conflagration can be replicated by particle accelerators, such as those at CERN in Geneva, our knowledge of the behavior of matter in these hostile conditions remains lacking. It barely spans the period of nuclear synthesis, and not much before either. Early on, physicists thought of the Big Bang as a useful model for their ideas. These days, it provides a testing ground for particle physics theories lacking much testing elsewhere. We must first grasp the development of particle physics over the past 40 years to appreciate how this has happened. Physicists have aimed to cover all aspects of nature in this century, so extending the field of science. Driven by revelations made possible by advancements in experimental technology, they have developed fresh theories of relativity and quantum mechanics. All events that can be tackled this way are explained by the four forces of nature. These four basic interactions enable the interaction among the several fundamental particles that make up all matter. Two of these, gravity and electromagnetism, have already been covered. The subjects of the other two are the weak and strong nuclear forces engaged in interactions among the nuclei of individual atoms. The four forces vary in type of elementary particle, involved in the interactions they control, as well as in strength. The strong nuclear force is the strongest, while gravity is the weakest. A phenomena uniting all known materials, electromagnetic forces bind electrons in orbit around atomic nuclei. But in order to precisely apply Maxwell's theory to atoms, scientists found early in the 20th century that they must take relativity and quantum physics into account. Extending Dirac's work, Richard Feynman and associates developed quantum electrodynamics, QED, a whole quantum theory of the electromagnetic force. According to QED, photons, also known as electromagnetic radiation, carry electromagnetic interactions between particles with different charges. Important properties of the basic particles between which these forces act define their nature. Fundamental properties define fermion particles. Their spin helps them to differentiate themselves from bosons, force carriers like photons. Two classes, quarks and leptons, split the fermions into three generations with two particles apiece. There are thus 6 leptons arranged in 3 pairs. For every pair of leptons, for example, one, sometimes known as a neutrino, has no charge. The electron carries one. The tau and mu, the other 2 charged leptons, decay rapidly and hence are far more difficult to detect than the stable electron. We charge all the quarks and pair off the 3 families. Not observing free quarks, the first family is defined by up and down, the second family by strange, and the third family by bottom and top. Composite particles, hadrons, always feature them. Among these particles are baryons made of 3 quarks, of which the neutron and proton are most familiar forms. Though there are many more hadron states, most of them are rather random. These short-lived, fast-decaying states could arise from accelerator tests or the Big Bang. Quarks have enough energy to break free inside a millionth of a second of the dawn of time. Sometimes earlier than this, the known hadronic particles dissolve into a soup of quarks. The opposite of any fermion is the antiparticle. The antiparticle of the electron is the positron. Also present are antineutrinos and antiquarks. The interactions among charged fermions are described by the QED theory. The next force to attract interest was the weak nuclear force in charge of the decay of some radioactive elements, including charged particles unable of sensing the QED interaction. All fermions engage in the weak interaction. Massive particles called W and Z bosons, not photons, mediate weak forces between particles, much as electromagnetic does. Unlike photons, these particles have mass, which helps to explain why the weak nuclear force acts only on the minuscule levels of an atomic nucleus. Apart from that, W and Z particles are gauge bosons, thus they behave in QED like photons. Extensively based on QED, quantum chromodynamics, also known as QCD, is the theory of the strong interactions holding quarks in hadrons together. Another set of gauge bosons in QCD moderates the force. We refer to these as gluons, and number 8 total. Furthermore, QCD exhibits a color quality akin to those of electric charge in QED. Drawing on Maxwell's seminal 19th century unification of electricity and magnetism, can we synthesize all of QED, the weak interactions, and QCD into a single comprehensive theory? In the 1970s, Glashow, Salam, and Weinberg developed a theory combining weak nuclear and electromagnetic forces. Electroweak theory holds that these two forces are low-energy representations of a single force. Particles can discern weak from electromagnetic forces. Physicists' theory holds that at high energies, the weak force and electromagnetic interactions show a symmetry that breaks at low energies. This results in separate appearances of electromagnetic and weak forces. Consider a straight pencil. It looks same from all sides when it is vertical. Should a passing truck or random air movement cause it to topple over, falling in any direction has equal chance. Still, it does it in a particular way and toward a certain direction when it falls. Likewise, the disintegration of high-energy symmetry in our planet could have coincidentally resulted in the variation between electromagnetism and weak nuclear forces. Strong and electro-weak interactions coexist in a combined theory of fundamental interactions, the Standard Model. Finding every main particle the Standard Model predicts is an amazing achievement, except from one. Unlike the electro-weak theory, which unites all three interactions, this model does not. The particular boson, the Higgs, needed by the conventional model to explain the masses is yet unknown. Physicists eventually want to unite all three forces covered thus far into a single theory known as Grand Unified Theory, or GUT. Of the several hypotheses that might support such a theory, it is unknown which one is accurate. A notion connected with consistent theories is supersymmetry. While the Standard Model treats the boson and fermion families differently, this theory implies an underlying symmetry. Every fermion has a boson partner in supersymmetric theories and vice versa. Squarks are the bosonic counterparts of quarks. Neutrinos are likewise. The photon's fermion companion is a boson, as is the photon itself. The cycle carries on when the Higgs boson interacts with the Higgsino. One amazing feature of supersymmetry is the likelihood that at least one of the many particles expected to arise at great energy is stable. Among these particles, one could be dark matter, ubiquitous in the universe. Particle theory considers symmetry as a basic idea. For example, the electromagnetic interaction equations have symmetric regard to electrical charge. Maxwell's electromagnetism equations would hold true even if we turned all positive charges to negative ones and vice versa. Although it is arbitrary to assign protons positive and electrons negative charges, reversing these assignments would not change the theory. Emphasizing the uncreated and unbreakable character of the electrical charge, this symmetry establishes a charge conservation law. Given our universe should have equal numbers of positive and negative charges, it is reasonable to expect a zero net charge. Surely this is the case. Moreover, the laws of physics lack distinction between matter and antimatter. Antimatter is, nevertheless, far less common than regular matter. More baryons, protons and neutrons than antibaryons, are specifically known to exist. A further kind of charge baryons have is their baryon number B. There is a net baryon number to the universe. One would have thought B should be a conserved quantity, much as net electric charge. B was thus never zero, if it is not zero now. Producing this asymmetry, or baryogenesis, stumped scientists working on the Big Bang theory for some time. Russian physicist Andrei Sakharov first proved that a baryon number need not be a conserved quantity and set the parameters under which a net baryon asymmetry could develop. His theory holds that the universe first had no net baryon number, but as it cooled, a slow inclination for baryons over antibaryon developed. Actually, the laws of physics have baryon-symmetric character. It is quite prophesiful since he studied long before coherent theories of particle physics emerged. He put out a mechanism whereby an early universe with 1,000 million baryons for every 1,000 antibaryons could result. A burst of electromagnetic radiation results when a baryon and an antibaryon collide and annihilate one another. According to Sakharov's model, most baryons would be destroyed upon antibaryon encounter. Thousands of millions of photons would ultimately exist in the universe for every surviving baryon. Actually, this is the case in our universe. Each baryon in the cosmic microwave background radiation comprises billions of photons. Though not the most dramatic, this description shows the junction of particle physics and cosmology. We will explore the theory of cosmic inflation, claiming that the geometry of the universe is shaped overall by subatomic physics. Exists either a finite or infinite universe? Following the Big Bang, will there be a big crunch? Does the universe really twist? The mass in matter of the universe is what? What kind of form this matter takes? Surely, one would expect a successful scientific cosmology to handle such basic problems. Mostly, the answers depend on a value known as O, omega. Astronomers have long battled measuring O depending on observations of the surrounding universe, with different degrees of success. Important developments in the development and application of new technologies suggest that in the next years the value of O could be ascertained. Still, the narrative has a sour turn. The most current data point to our perhaps incomplete understanding of the issue, though the exact value this quantity takes offers important hints about the structure of our universe on great distances and the very early phases of the Big Bang. The O problem is not just observational. Why then is the value of O so elusive and so vital? Consider how Einstein's general theory of relativity links the geometric traits of space-time, such as its curvature and expansion, to the physical features of matter, such as its density and state of motion, so clarifying what O means in cosmology. As was already mentioned, the cosmological principle makes using this intricate theory in cosmology easier. The Friedmann equation, a rather simple equation expressing the law of energy conservation for the universe as a whole, finally controls the development of the whole universe. Though the natural world contains many kinds of energy, only two are rather common. For instance, depending on its mass and speed, a projectile carries kinetic energy. Expanding the universe generates a lot of kinetic energy. All the galaxies are exploding. Another form of energy, and one more difficult to understand, is potential energy. An object has potential to gain or lose energy every time it moves and comes into touch with a force. Imagine a weight fastened to the end of a hanging string. One gets a simple pendulum from this. Rising the weight requires fighting gravity, thus doing this increases potential energy. I let go to start the pendulum swinging. By then the weight loses potential energy and gains kinetic energy. Maintaining total energy conservation, the system moves energy between the two kinds. The weight will move and swing to the bottom of its arc even without any potential energy. Eventually, it will show a complete cycle before stopping suddenly at the top of its arc to start yet another swing. At the top exist its maximum potential and lack of kinetic energy. The energy of this system is constant independent of weight. This law covers energy saving. Regarding cosmology, the kinetic energy is mostly determined by the Hubble constant ρ, sometimes known as the expansion rate. The potential energy of the universe is derived from its density or matter per unit volume. Unfortunately, this figure is even less certain than the value of the Hubble constant. It has no accurate estimate. Still, knowing ρ's value and the mean density of matter would allow us to ascertain the total energy of the universe. Friedmann equation or energy conservation law, demands this to be constant over time. Now, using well-known examples from high school physics, we can discuss the general evolution of the universe, independent of the technical difficulties related with general relativity. Consider the challenge of sending a vehicle from Earth into space. The gravitational potential energy of the vehicle is set by Earth's mass. The kinetic energy of the rocket we employ depends on its power. A slow launch with a small rocket's kinetic energy might not be enough to get the vehicle away from Earth's draw. The car thus rises momentarily before descending once more. The rocket uses kinetic energy to offset the potential energy required for its higher height, since of its great launch cost. A bigger rocket would fly farther before descending to Earth. At last, we will discover a rocket big enough to give the vehicle enough energy to completely escape the gravitational pull of Earth. If the rocket surpasses the critical launch velocity, it will keep on endlessly. If it falls short, it will crash back down. Usually we call this speed the escape velocity. In cosmology, the situation is similar, but the crucial number is the mass of the Earth, or more generally the density of matter, not the speed of the rocket, since this number is similar to the Hubble constant and is, hence, expected to be known. Consequently, considering a critical density of matter rather than a critical velocity is more advantageous. Should the real density of matter surpass the critical density, the universe will finally collapse. The gravitational energy of the universe suffices to slow down, stop, and reverse the expansion. Should the density drop below this vital threshold, the universe will keep expanding. Criticality has quite low density. The critical density depends on Ho and is arranged 1 hydrogen atom per cubic meter. Most modern experimental physicists consider such a low-density material as a great model of a vacuum. At last, let us introduce the number OOF, the ratio of the actual matter density of the universe to the critical value separating ultimate recollapse from infinite expansion. O'1 shows the dividing line. O1 indicates a universe that will finally recollapse into a big crunch. O1 shows an always expanding universe. Though more on that later, matter always slows the universe's expansion, thus these models predict a cosmic deceleration. This is true independent of the specific O value. Still, O is not the only determinant of whether the cosmological expansion will remain viable over long run. Though grounded in basic energy ideas from Newtonian physics, these arguments are not complete. The total energy density of the material determines the global curvature of space in Einstein's general theory of relativity. Models with key negative global curvature generate is smaller than 1. Negative curvature under an open universe model is if O is more than unity. One finds a positively curved, closed model. Between ultimate recollapse and infinite expansion, the traditional British Compromise universe rests in between and has O exactly equal to unity. Moreover, applicable to the flat geometry of this model are Euclid's theorems. That would be relief if this was the simplest choice the universe could have made. It is noteworthy to underline that the conventional Big Bang model does not forecast the value of O. This amount defines the geometry of space on cosmological levels as well as the ultimate fate of the universe. To accuse it as a useless theory, unable of addressing the basic problems with O, is unfair. As I have indicated, the Big Bang is a model rather than a theory. Though observationally and mathematically consistent, it is not complete as a model. This implies that it is a free parameter, same like the Hubble constant Ho. Stated differently, The mathematical equations of the Big Bang Theory explain the development of the universe. Nevertheless, to calculate a particular example, we need a set of initial conditions acting as a starting point. The basic mathematics of the model collapses at the beginning. Thus, we cannot theoretically correct the initial conditions. The Friedmann equation is well defined independent of the values of O and Ho. It is simply that our universe has been configured with a particular numerical combination of these values. Thus, at least not within the boundaries of the conventional Big Bang theory, and with what we know now, reason by itself cannot establish the cosmological parameters. Rather, observational data allows us to only deduce them. Still, there is also possibility to learn about the early universe using present cosmological observations. Early in cosmology, scientists understood the need of determining the cosmological parameters. Actually, a paper once written by renowned astronomer Alan Sandage, Hubble's research assistant, had the title Cosmology, the Search for Two Numbers. 20 years later, we still do not know the two numbers, hence knowing the several kinds of observations that could give us knowledge about O and the resulting kinds of results will help us explain why. We can classify the several types of observation into four main groups, even if there are many more ones. First comes the classical cosmological tests. These tests ascertain the curvature of space, or the rate of slowing down the expansion of the universe by means of far-off object observations. The most fundamental of these tests is to compare the ages of celestial objects, especially stars in globular cluster systems, with the ages projected by cosmological theory. The test is not yet a strong diagnosis of O, since, in the case of an expanding universe, the expected age depends much more sensitively on the Hubble constant than it does on O. Furthermore, it is unknown with any great degree of certainty the ages of old stars. Other classical tests directly look at the rate of acceleration or the form of space in the universe using the features of far-off sources. Hubble developed some of these techniques, which Sandage turned into a kind of art. The realization that the universe was expanding and its objects were changing rapidly threw them into disrepute in the 1960s and 1970s. One must probe great distances to measure the minute geometrical effects of spatial curvature. Thus one must inevitably view astronomical objects as their light first arrived on Earth. Cosmological observations usually provide ages more than 80% of the age of the universe. Thus, this could have happened long ago. We cannot ensure that far-off objects' brightness or size match those of nearby ones, since these features may evolve with time. Actually, we now mostly use classical cosmological tests to investigate the evolution of features instead of testing fundamental ideas of cosmology. Still, there is a rather notable and modern exception. The amazing outcomes of using supernova explosions as regular light sources show that the universe is not slowing down. The grounds for the following arguments are the nucleosynthesis theory. The agreement between observed elemental abundances and early universe nuclear fusion calculations provides one primary piece of evidence for the Big Bang theory. This agreement is only valid for very low matter densities, those less than a few % of the required critical density to flatten space. This is long known, and at first it provides a quite simple answer to every question I have asked. This argument does have a major disclaimer, though. This few % restriction only applies to nuclear reacting materials. The universe might be full of inert particles unrelated to the synthesis of light elements. Baryonic matter involved in nuclear events consists of two basic particles, protons and neutrons. Particle physicists have hypothesized that other than baryonic particles, The whirlpool of the early universe may have generated particles. Among these particles, some may have survived and represent some dark matter. The universe may consist in at least some of exotic non-baryonic particles. The great majority of cosmic material, whose type is yet unknown, could have a small contaminating stain like to that of regular matter from which we are derived. The Copernican principle gains significance from our inability to be the center of the universe and from our different makeup from most of the universe. Third kind of evidence consists on arguments from astronomy. Unlike the essentially cosmological measurements covered before, these arguments focus on particular objects rather than the properties of the space separating them. Weighing every component element separately helps us to find the universe's density. Assuming that gravity preserves the rotation of a galactic disk, one can use the internal dynamics of galaxies to ascertain their masses, much as it controls the motion of Earth around the Sun. The mass of the Sun depends on Earth's orbital velocity. The weight of a galaxy controls the orbital speed of its stars. We can also use this concept to even more massive systems and clusters of galaxies. These studies' overwhelming findings are that galaxies contain far more matter than what is apparent from stars such as our Sun. This is the well-known dark matter we deduce from its gravitational effects but cannot see. Furthermore, rich clusters of galaxies, systems consisting of large agglomerations of galaxies spanning more than 1 million light-years, have more matter than is usual of individual galaxies. Though the exact mass of the matter is unknown, plenty of data from the rich cluster systems suggests omega to be at least 0.1 in mass, if not more than 0.3. Tentative data from the dynamics of even more massive structures, such superclusters of clusters spanning tens of millions of light-years, suggests even more dark matter hiding in the interstellar medium. We investigated and verified these dynamical arguments by observing for ourselves how clusters alter the way gravity operates and by looking at the characteristics of the scorching gas-filling clusters with X-rays. It's interesting that the quantity of baryonic matter in clusters relative to their total mass appears to be far higher than what nucleosynthesis permits globally if the universe as a whole has a critical density of matter. Should this so-called baryon catastrophe materialize, either the total density of matter is far less than the critical value, or an unidentified mechanism must have driven the baryonic matter to cluster together. At last, there are hints from trying to understand how cosmological structure began, how the large bumps and irregularities of the universe could have developed in a universe that by nature should be smooth. More precisely, we will discuss how the Big Bang theories explain this phenomena. Most people grasp the foundations reasonably well. Still, the details are quite subtle and prone to prejudice and uncertainty. We have developed models almost exactly fitting all the available data. Others may achieve the same with far less than this O. Though this sounds terrible news, this study provides the solution for O. If we can measure these elements in more precisely, their characteristics in the microwave background will immediately offer the density of matter. It will also determine the Hubble constant, so avoiding all the tedious chores connected with the cosmological distance ladder. We hope the satellites meant to achieve this, MAP, NASA, and the Planck Surveyor, ESA, fly successfully in the next years. Current balloon tests seem to point to this as a likelihood. Based on the data, most cosmologists most certainly agree that O cannot be less than 0.2. Most of the universe depends on dark matter to have this lowest value. It implies that some must not be baryons, which comprise most of our daily stuff and exhibit protons and neutrons. Stated differently, one needs non-baryonic dark matter. About 0.3 is the value that many cosmologists choose. This seems to be in line with most observational evidence. Some have claimed that the data supports a density value close to the critical value. Hence, O can be quite near to unity. The growing astronomical evidence for dark matter and the theoretical realization that non-baryonic matter could be generated at very high energies during the Big Bang help to partially explain this. The major argument isn't only about personal viewpoints. It's also because determining the validity and consistency of, sometimes contradicting, observational data is difficult. The most often used theoretical rather than observational arguments support a high value, i.e., almost unity, for O. Although cosmologists could be tempted to dismiss such claims as prejudice, the great mystery the current Big Bang theory contains makes them very serious. Imagine yourself outside a closed chamber to grasp the core of this mystery. The room only features a small window that a small door hides. Nothing else is visible. They tell you to open the door just for a fleeting moment at a time, whenever you so want. Except for a man who started to walk the tightrope, suspended 2 meters above the floor, everything in the room is described as empty at an unknown point in the past. You also know that should a man fall, he will stay on the ground until you open the door. He won't stop if he keeps tightrope walking until you look in. What do you wish to find when you open the door? Your needed information relies on the man's position, that of the ground or the rope. If he performs for a circus, he could be able to walk up and down the rope for hours without falling. But his time on the rope would be rather short if he lacked experience in this area, like most of us do. Still, one thing jumps out rather obviously. Should the man fall from the rope to the ground, it will take a brief moment. Seeing the man descend the rope would thus surprise you. Given the situation, we should expect to find the man on the ground or the rope when we search. But, should you find him mid-tumble, you should be dubious. Although at first glance this has nothing to do with O, closer inspection finds a parallel. O develops in the conventional Friedman models in a quite unique manner. These models all point to a value that is arbitrary near unity and sporadic arbitrary near the Big Bang. Alternatively, refer to Figure 16. Regardless of the behavior at later times, all 3 seen curves get ever more similar near the beginning. Specifically, they approach the flat universe line. Models with an initial O somewhat larger than unity expand over time to reach values much beyond unity when recollapse begins. Reaching values of O very near to 0, values of O less than unity at the beginning of a universe, finally expand far faster than the flat model. In the latter case, the change from O to O near 0 is quick. Hence, this is most likely relevant considering the several signs that O is less than unity. The problem is clear now. For example, O quotient, say, 0.3, was rather lower in early cosmic history but near to unity. Indeed, the variation is rather tiny. At the 60th decimal place was the only way O could have strayed from unity at Planck time, or 10 bytes 43.3. Seconds following the Big Blast. O stayed close to the critical density state over time. It only lately started to fast deviate. Very shortly it will be quite near to 0. We seem to have captured the tightrope walker mid-air. To put it softly, this seems rather unusual. The incomplete standard Big Bang theory results in the cosmological flatness problem, a paradox. Considering the scope of the problem, many experts believe a complete solution is needed. Stretching the metaphor to its extreme, our universe could only escape the conundrum by assuming the position of a paid circus performer. O clearly is not close to 0, since there is strong evidence that it has a lower limit of about 20%. We so remove the man on the ground alternative. The next line of thinking is that something had to happen in the early universe for O to be exactly identified, since O has to be quite near to unity. Alan Guth's 1981 conjecture on cosmological inflation, that is, the very early phases of the Big Bang model, is supposed to have brought about this. Connected to inflation is a phase transition, a peculiar change in the properties of matter at very high energies. We have already come across an instance of a phase transition. One involves quark interactions occurring in the conventional model at 1/1,000,000th of the speed of light at the Big Bang. Quarks confine in hadrons. At low temperatures, at higher temperatures, they generate a quark-gluon plasma. Between lies a phase transition. Many unified theories allow a great range of phase transitions at even higher temperatures, indicating changes to the form and characteristics of matter and energy in the universe. Under some circumstances, a phase transition can also be accompanied by the manifestation of vacuum energy, an energy type existing in empty space. In this case, the expansion of the universe proceeds faster than in the conventional Friedmann models. Here we have cosmic inflation. Thanks in great part to inflation, cosmological theory has changed over the past 20 years. In this context, what counts most is that the fleeting phase of extravagant expansion flips the direction in which O would otherwise change with time. Unlike in the cases described above, inflation drives hard toward unity rather than away from it when it first starts. Inflation serves as a safety harness, guiding our tightrope walker back onto the wire each time he seems likely to fall. Understanding will be easier if one uses the already known link between space curvature and O. Remember that a flat space corresponds with a critical density and hence a value equal to unity. Should O differ from this magic number, space may curve. A highly curved balloon inflated to a great scale will seem to have a flat surface, much as the Earth. Inflationary cosmology holds that the balloon grows from a minuscule fraction of a centimeter in diameter to a scale larger than the known universe. Should the inflation theory hold true, we should get ready to live in a quite flat universe. Still, a near unity doesn't always point to inflation. Perhaps a different mechanism, may be related to quantum gravitational events, trained our universe to gently balance. Though rather important, these theoretical ideas cannot help to settle the argument. Against the intentions of theorists, cosmology is today empirical. Though observations take front stage, we could theoretically have cause to believe that O should be quite near to unity. Should O seem to be rather smaller than unity, should we give up on inflation? The answer is not always. One thing is that some inflation models developed by scientists can produce an open universe with a negative curvature. These models seem rather manufactured, thus cosmologists see them with mistrust. More importantly, hints point to a complex relationship between O and space geometry. After a long hiatus, the classical cosmological tests I discussed have returned. Two international teams of astronomers have been looking at the features of a particular type of supernova called a type Ia. The life of a big star ends suddenly with a supernova explosion. Supernovae are among the most astounding events in astronomy. For several weeks, they can outshine a whole galaxy and are more than 1 billion times brighter than the Sun. Observers have seen supernovae throughout recorded history. Inside the Crab Nebula, a cloud of dust and rubble produced by a supernova observed and documented in 1054, sits a pulsar, a rapidly rotating star. Renowned Danish astronomer Tycho Brahe reported a supernova in 1572. We recorded the last instance of this sort in our galaxy, Kepler's star, in 1604. Although old records indicate the Milky Way has 1 or 2 per century, We have not seen one of these explosions in practically 400 years. But in 1987, the Large Magellanic Cloud experienced a clear supernova explosion. Type 2 supernovae differ from Type 1 supernovae, according to spectroscopic studies, since they contain hydrogen, a component absent in Type 2 supernovae. Massive star explosions, in which the star's outer shell ejects into space and the star's core collapses into a sort of dead relic, directly generate Type 2 supernovae. The ultimate manifestation of an explosion would be a neutron star or black hole. Type 2 supernovas can collapse stars with different masses. Thus, their features differ greatly. We further classify the Type 1-tron supernovae into Type Ia, Eb, and Ic, depending on the details of their spectra. Particularly of interest are Type Ia supernovae. Their consistent peak luminosities follow from the same explosion. The conventional theory for these events is that companion star accretion causes mass acquisition for a white dwarf star. When the mass of the white dwarf exceeds a critical mass known as the Chandrase-Chandrase. Chandrase, 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 Chandrase Chandra mass, roughly 1.4 times that of the Sun, the central parts of the white dwarf collapse and its outer parts explode. We expect these objects would always release the same energy, since the explosion mass is always near to this critical value. Because of their regular characteristics, Type Ia supernovae are very promising objects for estimating the deceleration rate of the universe and space-time curvature. New technologies let astronomers hunt for and find Type Ie in galaxies with redshifts near one. By means of comparison with nearby supernovae, the observed brightness of distant supernovae can be utilized to project their distance from us. Remember that the universe has expanded by a factor of 2 while light flows from the supernova to us. We can thus ascertain the degree of slowing down of the universe, roughly the time it takes for light to reach us. The trouble is that these supernovae shouldn't be fainter than they are if the universe is slowing down. The cosmos is not slowing down at all. It is rather expanding. This observation questions the basic principles of the Friedmann equations, which offer the accepted cosmology theory. These models have to all slow down. Not even the members of the Friedmann family with low O should accelerate, since their low density results only in a minor deceleration. The critical density models that inflation seems to favor should show significant slowing down. In what went wrong? Though they are still debatable, the supernova observations I have been talking about point to a significant change in cosmological theory. Einstein himself, though, created a ready-made fix for this flaw. I discussed how Einstein's original theory of gravity underwent changes in cosmological constant. He took this action, one he later came to regret, to create a theory explaining a stationary or non-expanding universe. His cosmological constant changed the law of gravity such that space neither expanded nor contracted. Applying the cosmological constant in a modern environment can render the law of gravity repulsive on vast distances. By means of this, a cosmic repulsion overcomes the gravitational attraction of matter, so accelerating the universe's expansion. This cure requires an acceptance of the cosmological constant as not a negative idea in first place. Modern theory, however, presents a different view on how this might happen. Initially found in the space-time curvature and gravity mathematical equations of Einstein's original theory, the cosmological constant indeed, that marked a modification in the gravitational law. Still, he could have wrote this term on the other side of his matter theory equations. Conversely, his equations contain the notorious Einstein cosmological constant, which explains the vacuum's energy density. Though it sounds unusual, this movie features an energy-filled vacuum already. One needs exactly this kind of vacuum energy in inflation. Early versions of cosmic inflation theory hold that once the brief period of hyperexpansion ends, the vacuum energy expelled by a primordial phase transition vanishes. Only a small fraction of this energy has thus far persisted, though. This is the energy that has made gravity push rather than pull. Evidence points to this energy perhaps being much less than the unit value needed for flat space. This conforms with the inflation hypothesis, since vacuum energy could induce acceleration. Though being perverse in that gravity pushes rather than pulls, at least the vacuum energy curves space in the same manner as ordinary matter. In a universe comprising matter and vacuum energy, flat space can exist without the slowdown required for a normal Friedman model. Still unresolved are vacuum energy, the value of O, and the acceleration of the universe. Still, during the last few years, these ideas have spurred a lot of theoretical and experimental activity. If successful, all of these questions could be answered by fresh generation of measurements. Galaxies are the basic building blocks of the universe, but they are only some of the most prominent visible constructions. Like other people, galaxies form social groups instead of being by themselves. We investigate the galaxy distribution over cosmological distances using the large-scale structure. First, we must explain the source of this structure, which is a hot issue in modern cosmology. Usually used in spectroscopic studies, Hubble's law estimates the distances to galaxies from their redshifts, guiding the distribution of matter on a vast scale. Many years before redshift studies were feasible, the structure was well known. The first thorough study of galaxy locations, the Lick map, clearly shows this highly non-uniform distribution of galaxies in the heavens. Though this map is quite remarkable, it isn't easy to ascertain whether the buildings are real, physical, or only the outcome of random projection effects. Even though everyone is familiar with the constellations, these are not actual physical relationships. They illustrate the stars' distances from the sun. Thus, the main tool for cosmography has become the redshift survey. One often used example of this approach is the Harvard-Smithsonian Center for Astrophysics, CFA survey, which published its results in 1986. This analyzed the redshifts of 1,061 galaxies found in a constrained sky area during the 1961 Palomar Sky Survey. Later, the same team enlarged this survey to include several more strips. Seeing every galaxy with a telescope designed for redshift surveys was slow and demanding in the 1990s. The method consisted of obtaining a spectrum, calculating the redshift, and seeing the next galaxy. Resource competition meant obtaining several thousand redshifts, which needed months of telescope time, usually over several years. The development of multi-fiber devices on wide-field telescopes allows astronomers to record up to 400 spectra at a single telescope point today. Using the Anglo-Australian telescope, Australia and the United Kingdom carried out one of the most recent redshift studies, the 2-degree field, 2DF, survey. This will eventually map the positions of roughly 250,000 galaxies. The broad term used to characterize a physical grouping of several galaxies is a galaxy cluster or cluster of galaxies. Systems housed inside clusters can vary greatly in scale and complexity. For example, of the relatively small group of galaxies known as the local group, the Andromeda galaxy, M31, is the only other significant member of which our galaxy, the Milky Way, belongs. At the other extreme are the so-called rich clusters of galaxies, sometimes called Hubble clusters, which comprise hundreds or even thousands of galaxies within a few million light-year radius. Two well-known instances of such entities nearby are Virgo and Coma clusters. Different densities allow systems to distribute galaxies hierarchically, fractally, or roughly between these extremes. The densest Abell clusters are collapsed objects held together in equilibrium by their self-gravity. Although we might not be bound, in this sense, by less rich and more widely spaced systems, they reflect a general statistical tendency of galaxies to cluster together. Galaxy clusters alone do not now make up the biggest structures in the universe. Galaxy distribution is rich on scales over 30 million light-years. New observational studies indicate that galaxies come in a range of forms. Like the Abell clusters, they can be essentially spherical blobs. They can also be long, roughly linear structures called filaments, or flattened, sheet-like constructions like the Great Wall. This essentially two-dimensional concentration of galaxies was found in 1988 by Harvard-Smithsonian Center for Astrophysics scientists. Less than 20 million light-years thick, the Great Wall has dimensions of at least 200 million light-years by 600 million light-years. It boasts hundreds of galaxies and a mass of at least 10^16 solar masses. Superclusters, huge, loosely bound agglomerations, arise from rich clusters. Many have anywhere between 10 and more than 50 rich clusters. The most well-known supercluster is the Shapley concentration. The closest is the local supercluster, which, as already noted, is centered on the Virgo cluster, a flattened structure in the plane along which the local group is traveling. Superclusters are well known to span up to 300 million light-years and comprise material equivalent to 10 to 17 solar masses. Vast, almost empty areas complement these constructions. Many have a roughly spherical form. These so-called voids have none or less galaxies than the average. Large redshift surveys on scales of up to 200 million light-years have identified voids with less than 10% of the average density. Large voids are not surprising given the existence of massive galaxies and supercluster clusters, since regions with densities higher than average can only exist because regions with less than average must first be created. Large-scale structural mapping lends the impression of a vast cosmic web, a complex network of intersecting chains and sheets. Still, how did this complexity develop? Assumed to be featureless and smooth, the universe is hence based on the cosmological principle in the Big Bang theory. Luckily, the structure fades on sizes beyond the cosmic mesh. This confirms observations of the cosmic microwave background from about 15 billion years ago from the early universe. The cosmological principle fits this almost homogeneous microwave background in the sky. That is almost, but not exactly. Using its sensitive detectors, the COBE satellite started mapping and spotting changes in the microwave background temperature of the heavens in 1992. The microwave background looked isotropic in the sky when first discovered in 1965. Later on, researchers discovered a broad temperature fluctuation across the heavens of about 1 part in 1,000 degrees. We now realize that the radiation field left over from the Big Bang produces this Doppler effect on Earth. From our point of view, the sky is somewhat colder where we are now and warmer where we are heading. Still, the radiation came from all directions equally, notwithstanding this dipole variation. Still, theorists have long felt the microwave background should show a rippling pattern of hot and cold splotches. Newspapers carried stories about these trends worldwide once COBE identified them. Why, then, is the microwave's background not seamless? As it always does in cosmology, gravity links the roots and solutions of major constructions. Friedman answers tests and large-scale structures by stressing how the mass characteristics of the universe change. Friedman's theories, however, are illogical since they offer an absolutely flawless universe. This universe starts this way. Thus, it will always be perfect. Still, a real-world environment is always full of imperfections. Rarefied areas and those somewhat denser than usual could exist. In what way does a somewhat lumpy universe behave? The idealized picture is very different from the real response. A denser section of the universe pulls on its surroundings more forcefully than usual. It will thus often attract material in, so reducing its surroundings. It becomes even denser than usual in the process and pulls harder. This causes gravitational instability to spiral out of control, producing tightly bound lumps that finally unite to form filaments and sheets resembling those on maps of the universe's structure. Gravity magnifies minuscule initial ripples into massive density changes, much as a strong amplifier would. Galaxy surveys help us to map the ultimate outcome. The COBE map shows the initial input. We even have a strong hypothesis to explain the imprinting of the first fluctuations of cosmic inflation. Although the general concept of how structure forms has been known for a long time, the complicated behavior of gravity makes it challenging to translate this knowledge into exact predictive computations. Only symmetric simplification will help to solve even Newton's laws of motion. Late phases of gravitational instability do not offer any such simplicity. Maintaining awareness of all the forces at work everywhere and on everything is crucial, since everything in the universe presses on everything else. Solving the involved sums with pencil and paper is too difficult. However, the field developed faster when big computers became available in the 1980s. Though gravity could create cosmic structures, success would depend on a lot of mass. Theorists have concluded that normal matter is not allowed to play a major role in primordial nucleosynthesis arguments. Hence, strange dark matter not involved in nuclear reactions rules the universe. Simulations indicated that cold dark matter was the most appropriate kind. If the dark matter were hot, it would move too quickly to arrange into the proper-sized clumps. Many years of computer time later, a picture emerged, displaying the bottom-up development of cosmic structure. Little dark matter clusters first form. These building elements then mix to create larger units, and so on. Eventually, objects on the scale of galaxies develop. When gas, which consists of baryonic elements, falls into space, it forms galaxies. Galaxy grouping into chains and sheets marks the continuation of the hierarchical development of structure. In this picture, structure changes rapidly with time, that is, more precisely with redshift. Though clearly successful, the idea of cold dark matter is still unfinished. Dark matter's composition and mass are yet unknown. Furthermore, the question of how galaxies develop is unresolved, given the complex hydrodynamic and radiative processes connected with gas motion and star formation. Still, theory and simulations are not the only tools in this field nowadays. Thanks to developments in observational technology, including the Hubble Space Telescope, we can now closely study how galaxies' characteristics and spatial distribution have changed over time. Thanks to the forthcoming generation of massive redshift surveys, we will have a remarkably thorough knowledge of the patterns of galaxies in space. This also clarifies the formation mechanism of galaxies and the dark matter concentration. Nevertheless, the answer to this problem starts at the beginning, instead of depending on observations of the ultimate result of the gravitational instability process. This experiment had many restrictions. Even if the COBE satellite represented a major breakthrough in structural development studies. The main drawback of COBE was its incapacity to clearly solve the complex ripple structure in the microwave background. Astronomically, COBE's angular resolution was only roughly 10 degrees, quite coarse. By contrast, the full moon's diameter is about 0.5 degrees. Cosmologists hope to find many unresolved questions about the fine structure of the microwave sky. Early on in the universe, ripples in a sound wave were created when the temperature was quite hot, many thousand degrees. The universe hummed with sound waves that moved both backward and forward. The sun's surface vibrates with the same frequency and temperature. COBE's low resolution allowed it to only detect ripples with a rather long wavelength. These are rather low-pitched sound waves, the bass notes of creation. These waves might have a more interesting sound and carry vital data requiring more nuance. Still, the universe should generate a far more interesting, higher-pitched sound. Sound waves travel at a specific speed. This translates in the air to roughly 300 meters per second. In the early universe, the speed of sound is far faster, almost as fast as light. About 3 million years into the history of the universe, the microwave background forms. Since the Big Bang, presumably during their first excitation, sound waves have only been roughly 300,000 light-years away. The oscillations of this wavelength create a unique note, almost like the fundamental tone of an instrument. This great cosmic fanfare produces superclusters of galaxies roughly this scale by design. Although the early universe's signature wavelength should be evident in the pattern of hot and cold spots on the microwave sky, its short wavelength causes it to show on a far smaller scale than COBE can resolve. The spots it generates have an angular scale of roughly 1 degree. Scientists have been racing to design tools able to detect the higher harmonics and fundamental tone of the universe since COBE. We aim to solve many of modern cosmology's primary problems by carefully analyzing creation's sound. The sound spectrum reveals the mass. Cosmological constant presence is shown. Hubble constant value is revealed. Curvature of space is revealed. Inflation possibility is revealed. 2 major experiments, the NASA-led MAP mission scheduled for launch in 2001 and the Planck Surveyor of the European Space Agency scheduled for launch a few years later, will produce high-resolution maps of the ripple pattern in the sky. Correct interpretation of these structures should lead to clear answers soon. One senses real excitement